All right, hi, baby Patrick. All right, here you go. Here is your 12-word seed phrase. Now, you're going to need that in order to generate your private key, which you're going to use to sign all your transactions. Now, just remember, if you lose your seed phrase or you lose your private key, you won't be able to send any more transactions ever. And if you accidentally expose or leak your key or seed phrase, whoever gets it will be able to spend all of your money. What? This is how a lot of people feel when trying to get their friends into crypto. They tell them that they have to follow all these very difficult rules, and if they break one of those rules, they're going to get rug pulled for all their money. So the wallet user experience for getting into crypto isn't great. Private keys can be very difficult to handle. Anything you want to do costs gas. Preserving privacy from your wallet can be difficult. Sending multiple transactions at once rely on you interacting with a middleman smart contract. There are a lot of issues with current private key and wallet management, and account abstraction is here to try to help aid those. Account abstraction can be boiled down to one single thing. In a traditional transaction, you need to use your private key to sign the data to send the transaction. With account abstraction, you can sign the data with anything. To reiterate, normally we validate transactions by signing them with our private key. Imagine being able to sign a transaction with your Google account, with your GitHub account. A transaction can only go through if 3 of your buddies give you a thumbs up. You can only sign a transaction during the day. You can't surpass some type of spending limit. So one more time, just to drill it in. Historically, private key equals wallet. With account abstraction, whatever the hell you want is a wallet. And with this whatever the hell you want, with this customization, this means that we can additionally have other people pay for our transactions. Right now, if you want to do anything on chain, anything at all, you always need to have at least a tiny bit of gas, and sometimes depending on the chain that you're working on, getting that tiny bit of gas can be a huge pain in the butt. But account abstraction can help solve this. So if I really want to give baby Patrick his first wallet, Goo Gaga, I can actually code in some parental controls where he can create all the transactions and then I have to approve them. And all of his super likes on Skibbity Toilet, I will definitely be approving. So this all sounds fine and dandy, but how does it actually work? Now, getting into this is where this gets a bit complicated because there are two places where account abstraction exists. As of March 1st, 2023, the first official account abstraction smart contract was deployed to the Ethereum mainnet called the IEntryPoint.sol, and you have to interact with this smart contract in order to do this account abstraction thing, and other chains like ZK Sync have this natively baked in. So let's first learn how this works with Ethereum, which doesn't have it natively baked in, and then we'll look at how it works with ZK Sync, which has what's called native account abstraction. In a traditional Ethereum transaction, you take your MetaMask or your Rabby or whatever wallet you're using, you sign a bunch of data, you spend some gas, and you send this on chain, and the Ethereum node will be the one that will add this transaction to a block in the blockchain. Right? This is pretty well known. Whenever your MetaMask pops up, any of these transactions in here are you sending a bunch of data that you signed with your MetaMask. Your MetaMask did the signing, send it to an Ethereum node, and it adds to a block. But as we've been saying, private keys are really sucky. So how can we have an account without having to deal with private keys? Well, you still kind of do have to deal with a private key, and on Ethereum, first thing you have to do is you have to deploy a smart contract that defines what is the thing that can sign transactions. So you have to deploy some type of smart contract first to the blockchain. Whereas previously, only private keys could sign transactions, but you could say all of my friends have to sign the transaction with their private keys, or the friend's cast has to. You could use something like a Google session key to be the one to sign transactions. If you can code it, you can build it. So this smart contract will be your new wallet, and you will have a smart contract wallet. So now you might be asking, okay, cool, but how do I send a transaction through my smart contract wallet that is deployed? Will it pop up in MetaMask for me? Well, this is where it gets a little bit more complicated. So now just remember, traditionally, you use your MetaMask, you use your private key to sign some data, and then you send it to an Ethereum node. And now the main difference is you are no longer sending your signed transaction, your signed data to an Ethereum node. You're gonna send this someplace else now. Now, with account abstraction, you'll sign your data with whatever you use to sign it. It could be Google, it could be your friends, whatever. And you're gonna send something that's called a user operation to an alt mempool. So according to ERC 4337, which is the EIP/ERC for this, you'll actually send this thing called a user operation, which has all this additional transaction information. And you're not going to send this to the blockchain. You're instead going to send this to something called an alt mempool. And this is still going to be all off chain. This alt mempool is basically just any group of nodes that are facilitating these user operations. So this is why you actually don't have to spend any gas when you sign and send this transaction because you're actually not sending it to an Ethereum node. So there's a chance that you're not even going to be making transactions in your MetaMask when you send to this alt mempool. For at least on Ethereum, working with these alt mempools, these account abstraction accounts, the wallet UX is going to have to become a little bit more clever to deal with this. Now, these alt mempools, they are going to be the ones to actually pay some gas because what they're going to do is they're going to take your user operation, they're going to validate it themselves, they're going to make sure everything looks good, and then they are going to be the ones to actually send your signed transaction on chain. So it's the alt mempool nodes that are going to be sending the transaction and doing the traditional Ethereum transaction. So in Ethereum, account abstraction, or ERC 4337, is just a framework that everyone's agreed upon for sending these user operations. So these alt mempool nodes are going to be the ones to send this transaction, and they're going to send it to this thing called IEntryPoint.sol. A group called ETH won a grant from the Ethereum Foundation to be the one to create and deploy this contract. It's this team that actually has deployed this EntryPoint v07 on chain to Ethereum, Optimism, Arbitrum, Polygon, blah, blah, blah. And so it's this address, it's this smart contract that handles every single account abstraction user operation sent. All of these alt mempool nodes calling this contract call this function called handleOps, where they pass all the data associated with a user operation, which includes pointing to your smart contract account that you deployed. So these alt mempool nodes are going to deploy your contract for you. It's going to always be routed through this EntryPoint.sol, which is going to do some validation. And then it's going to be routed to your contract, your smart contract account, which is where everything will be directed from. So when you work with an app, when you send a transaction to something like Aave, your account will be the message.sender or the from account here. And it'll go through all the logic that your account set up. So for example, if you set it up so that only Google could sign keys, if Google didn't sign the key, this whole transaction here sent from the alt mempool nodes would revert. And then of course, once everything's included, your transaction will be added to the Blocksys blockchain. Now, there's a couple things here. There's a couple of things called add-ons. One of them is a signature aggregator. This is where it aggregates. This is an optional add-on to account abstraction where this entry point will let you define a group of signatures that need to be aggregated. This is where you can have like your friends be on your multisig. And then there's also this thing called a paymaster, which this is where it gets really cool, where you can set up your code base to have somebody else pay for the transactions. So the alt mempool nodes, of course, will pay for the transaction to actually send it. But then you can set up a contract called a paymaster, which will just have the logic of saying, hey, so-and-so is actually going to pay for my transactions here. And you defined all of this in your account. You set it up as such. Now you might be thinking, oh, okay, cool, Patrick. Well, I'm always going to do this if the alt mempool nodes are always going to pay for my gas. Well, if you don't have a paymaster, the alt mempool nodes will pay for your transaction, but they will only pay for the transaction if one of these accounts on chain is going to pay for it. So if you don't have a paymaster set up, it'll try to pull funds out of your account. And that's how the whole system works here. So simple in concept, very convoluted in practice here. Now, this process obviously involves a lot of different steps, a lot of different moving parts. You have to send to these alt mempool nodes. They're going to be the ones to send to the on-chain entry point. You have to customize your account and blah, 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 do all this stuff. Some chains have said, you know what? Let's just do this natively. ZK Sync is one of these chains where they combine this process together. Let's look at how ZK Sync does account abstraction. For ZK Sync, the process is going to look really similar. You still have to deploy a smart contract that has all your rules codified. But the main difference is that the alt mempool nodes are also the ZK Sync nodes. So we actually get to skip this step of having to send our transactions to this alt mempool because the ZK Sync nodes also work as alt mempool nodes. The reason ZK Sync can do this is because they have what's called default accounts for every single account. Every single MetaMask account, every single account in ZK Sync is technically a smart contract account that has very specific functions and behaviors that can be validated. So anytime you interact with any address, it will always assume it's a smart contract because that's just how they work. So what I'm showing you here is their default account smart contract. Anytime when you load up ZK Sync into your MetaMask and your addresses are automatically created, they are automatically connected to these default accounts. And this is what the code of those addresses look like. I've got a video coming out next where we're actually going to create some account abstraction accounts on both Ethereum and ZK Sync so you can see exactly what they look like and how they flow and how everything fits together. So be sure to watch that as well if you want to learn how to actually code these things. And hopefully we can save baby Patrick from having to deal with his private keys himself. Thanks for watching, and I'll see you next time. All right, y'all. In this video, we're going to be actually walking through building some minimal account abstraction accounts. Now, we're actually going to be doing it two different ways. We're going to be building one for Ethereum and one for ZK Sync. Why? Because Ethereum and ZK Sync do it slightly different. For Ethereum, whenever you send a transaction via account abstraction, you actually have to send it to this alt mempool. For ZK Sync, there is no alt mempool. You just send it via the normal mempool. You just have to specify your transaction as a type 113. If you want to follow along, obviously the code here is going to be at cypherin/minimal account abstraction right here. You can follow along here. And we're going to be creating two smart contracts. One is going to be minimal account. You can see this account right here. Very, very minimal smart contract. It does almost nothing interesting. All it really does is it allows for either our private key to pay for the transactions or this smart contract itself to pay for transactions. It's incredibly minimal. We didn't add any interesting functionality in here. But as we go along and build this, we'll show where if you wanted to add additional customization, for example, maybe adding a paymaster or a signature aggregator or some type of spending allowance or a Google session key, whatever, as we build this out, it'll become clear where you can expand on this and build them yourself. Then additionally, we also have in ZK Sync here, we're going to have our own custom ZK Sync minimal account as well, which is going to be slightly different. And in doing this, we're actually going to learn a ton about ZK Sync as well, because the ZK Sync ecosystem is actually very different than the way the Ethereum ecosystem works. Because like I said, you actually don't have to send your transactions to an alternate mempool. You can just send them directly to the exact same mempool you always do. And ZK Sync has it built into the actual layer 2 to handle all these transactions. So if you go to the README associated with this, and we scroll down to example deployments, we can see here we have a ZK minimal account on ZK Sync Sepolia. We have one on Arbitrum as well. If you want to go check these out, you can check them out here. But what's cool is we have two transactions here where we have the approve function where the from on ZK Sync, and this is what's really cool to me, where the from is actually going to be this ZK Sync minimal contract here. Now it's not actually verified because the contract verification for some of the parameters that we're going to be using doesn't work quite yet. But what makes this so crazy is that you can't have a from be a smart contract in the Ethereum ecosystem, but in ZK Sync you can. So for our Arbitrum example, this is still really cool. So the from is going to be one of these bundlers, one of these alt mempool people. This is going to be similar to what you would do on Ethereum. Our from is not going to be our smart contract wallet. However, we were able to interact with our smart contract wallet as if we were sending the transaction. So all this did was submit an approval to the USDC token. And during this transaction, the message.sender was our smart contract wallet. So very cool. We're going to be building both of these. And this is going to give you the power to create any type of flow that you want for your smart contracts. If you want people to send transactions with a special session key that you create, great. You can create a smart contract that does it with this process. If you want to create a super special multi-sig where you and a bunch of friends and a certain passcode have to be the ones to get together and send a transaction, great. This is how you're going to learn how to do that. And you're going to learn how to do it for both Ethereum and ZK Sync, which is going to be awesome. So let's jump into it. We are going to start building with Ethereum first, and then we're going to build with ZK Sync so that we can really understand the differences. And as we do ZK Sync, we're going to learn a ton. So let's get froggy. All right, so here we are in our brand new blank VS Code where we're going to create some account abstraction wallets. You are going to learn a ton in this section, and I'm incredibly excited for you to come along with us here. This is probably going to be one of the more advanced projects that you make in your learning journey, but let us begin. So we want to just first make sure we are on Foundry. So I'm going to do a quick Foundry up, make sure we're on the latest version of Foundry here, get everything downloaded, and then we're going to go ahead and do a little forge init, create our basic project here, and great. So we have this set up. So let's go into our source. Oh, let's actually go into source, script, and test. Command click or control click. Let's delete all these. And we're going to go ahead and create a brand new file. Actually, no, screw that. We're going to create a new folder called Ethereum. And then we're going to create a new folder called zk-sync, right? And right in the README here, let's delete everything. Say about, what are we going to do? Number one, create an AA or account abstraction account on Ethereum. Let's just say a basic one, right? And then number two, create a basic AA on zk-sync. Deploy and send a user op/transaction through them. So we were going to deploy these, send a user operation or transaction through them, and really see the whole process end to end. Note, I'm not going to send an AA to Ethereum, but we will send an AATX to zk-sync. So we're actually just going to send our transaction directly to Ethereum because kind of showing the account abstraction I don't think is that interesting, but I do think it's interesting on zk-sync. But we are going to still send a transaction through our smart contract wallet on Ethereum. It'll make sense in a minute, I promise. So let's go ahead. Let's get started working with Ethereum here. So in our Ethereum folder, we're going to create a minimal account.sol. And this is where we're going to start. You already know the drill. We're going to set up a little pragma here. MIT 0.8. Let's do 24. Contract minimal account like this. So here's where we are. And the first question is, okay, what the hell do I need to do? And this is where we could go over to ERC 4337 and figure out, okay, what are these smart contracts even supposed to look like, right? Because we know we're supposed to be sending transactions to this alt mempool nodes, and they probably need to be formatted a special way. And then we need to send it to this EntryPoint smart contract, which will then send it to our contract. So there's probably some very specific functions that need to be called for this process to work correctly. So let's figure out what those functions are so that our process can work correctly. Now, if you go through the EIP itself, you'll find what is needed for like a user operation. And this is the data that needs to go to the alt mempools. You'll also find the EntryPoint definition. This is what we need to be worried about because this is when passed to on-chain contracts, the EntryPoint contract, and then to account and paymaster, a packed version of the above structure is used. So when you're sending data to an account abstraction alt mempool, this is the data you need to send it. But when you're sending data to either this EntryPoint contract, right? Because every single one of these user operations flows through this EntryPoint contract, you need to send all this data. And again, if we look at the EntryPoint contract itself, we go to write contract, we know that this is where every single user operation is going through. It takes ops, which is a tuple, and a beneficiary address here. So we can even go to etherscan.deth.net here, just really see what this is. So etherscan.deth.net is a way to kind of see a smart contract right in your browser from Etherscan. We can look up function handle ops like this, and we can see the handle ops. It takes a packed user operation and an address payable. So whenever we send our data to these alt mempool nodes, we need to send it so that they can send this packed user operation stuff. And where are they getting this packed user operation stuff? Well, there's another smart contract called packed user operations.sol, and there's this struct. So we need to send all the data about our transaction in this packed user operation. We need to pick the sender, the nonce, the initialized code, call data, all this other stuff. And the signature is really this customization piece where we can kind of define how we want to define signatures, right? Because again, account abstraction, you can sign anything with anything. If you can code it, you can build it. So we need to figure out what this contract needs to look like. At some point, the EntryPoint contract is going to call this contract, and we need to set this up correctly. Now, right in the EIP, they talk about having this account contract interface. The core interface required for an account to have is going to be this function validate user operation, where it takes this user operation, takes the user operation hash and this missing account funds bit, and then returns whether or not the user operation is valid. Back in this image here, whenever these alt mempool nodes call this entry point is going to call your account, and your account is going to say, hey, this transaction is valid or it's not valid. If it's not valid, it'll revert. The alt mempool nodes won't be able to send the transaction. And if it is valid, then the alt mempool nodes will be able to send the transaction for you. So we need to make sure our validation is spotless, and this is the function that will do it. So we could 100% add this in here ourselves, but what I actually want to do is I want to import from this Infinitesium account abstraction project here. I want to import this whole thing as a package. That way we can use their interfaces and any other cool stuff that they've built, we can use it in our code base. So we're going to go ahead and copy this, and I'm going to be using version v07 for our code base here. So if you want to make sure to follow along, that's the version that we are going to be using. So back in our code base, we're going to do a little forge install, paste that in here, and then do a little @v0.7.0 -- no-commit. And now we're going to go ahead and install all of that as a library. In our lib, we have that account abstraction chunk in here. And they have an iAccount, so we can actually just import that ourselves. So we're going to say import iAccount. They have that account interface as defined by the EIP here. So we'll say iAccount from lib/account abstraction/contracts/interfaces/iAccount.sol. I already know where it is, so cool. And then we'll say contract minimal account is iAccount, so that we don't miss any stuff. And if we command click or we go to this contract here, we can see down at the bottom we have this function validate user op, which is exactly what the ERC/EIP specified. And then we have all the information here on what this function actually does. If you want to pause and go through this, feel free, but we're going to explain it as we go along here. So we do know at some point we're going to need to add this. So I'm just going to go ahead and pop it in here right now, and then just make it like blank here to do this. Now, we're going to need this packed user operation object as well. So we're going to have to import that as well. So I'm going to say import packed user operation from lib/account abstraction/contracts/interfaces/packed user operation.sol, like this. And if we command click on this or control click on this, you can see we automatically get this struct pulled in here from this contract. Well, this technically isn't even a contract. This is just kind of like a floating struct here. But in any case, we get it into our code base here. And really at the end of the day, this is the most important thing that we need to flesh out. So let's actually just start with this, right? Because this smart contract is going to be an account, and this validate user operation is essentially the validate signature, right? What the EntryPoint contract is going to send to us is this packed user operation. This packed user operation is going to have like, hey, call USDC and set it to approve, and here's the signature, blah, blah, blah. But also they're going to give us this user OP hash, or the user operation hash. It's going to be the hash of the entire user operation, and it can be used as the basis for a signature. So in the user operation, in this user op, in this packed user operation, they're going to have the signature, and we need to figure out from the signature that they give us and the hash that they give us, okay, does it actually match? And then missing account funds is going to be missing funds on the account's deposit in the entry point. And this is the minimum amount to transfer to the sender, basically to the entry point, to be able to make this call. So you can kind of think of this as like the fee, basically. And this is how these alt mempool nodes are going to get paid after they send these transactions, because they don't want to send it for free, right? So let's go ahead and start actually validating a user operation. And let me just dive into this packed user operation for a second. So the sender, this is where it's going to be, you know, our minimal account. They're going to say, hey, I want the sender to be this minimal account, this account abstraction account. The nonce should be like a number only used once. You can almost think of it as like the sequence of transactions in the transaction. We can ignore this for now. This is, if we set this, the account contract will be created by, this is like a constructor, the call data, and this is where we put like the good stuff, if you will. This is where we say, hey, our minimal account should approve should approve USDC for 50 tokens or something. Should call the approve function or transfer or like whatever. This is like the actual meat of the transaction. Account gas limits is obviously gas limits. Pre-verification gas. This is some more gas stuff. Gas fees, more gas. These are all to handle the different gas fees, basically. Payment and data. So in this image here, again, so by default, your account is going to have to pay the alt mempools for the funds, right? Your smart contract. There need to be funds in here to pay for it. However, if you've set up a paymaster, if you've customized somebody else to pay for your transactions, this is the data that needs to be sent as such, and obviously the signature, and we're going to sign this whole chunk of data up here, and we're going to customize in our smart contract here what is a valid signature. So cool. Hopefully that makes sense. Let's keep going. Let's actually start there. So the first thing we're really going to care about is we're going to want to validate this signature in here. So I'm actually going to create a custom function called _validate signature. And we're going to take this user operation and this user operation hash. So in our packed user operation, they have this signature, and we need to validate this signature against all of this. Let's really quickly figure out how we want signature validation to work. This is, again, where your creativity can run free. I'm going to be super lame and basic. I'm just going to say a signature is valid if it's the contract owner. That's it. So if it's the minimal account owner. So that's it. So whoever deployed this contract also gets to be the only one who sends transactions through it. So it's a little bit lame because basically we're like, all right, MetaMask, you need to call this smart contract wallet in order to call anything, kind of like just adding an extra step, but it'll show you what we intend here. So we're going to say import ownable from OpenZeppelin, and we should probably install some OpenZeppelin then, shouldn't we? So I'm going to go ahead, I'm going to install OpenZeppelin. I'm going to do forge install OpenZeppelin / Zeppelin contracts. And I'm going to be using at 5.0.2 -- -no - commit for this one. So if you want to follow along with me, also install 502 it's v502, sorry. And it looks like those are in. And then I want to update my foundry.toml real quick to do some remappings. We're going to say remappings equals at OpenZeppelin / contracts equals lib / OpenZeppelin - contracts, like this. And now we should be able to get at OpenZeppelin / contracts / access / ownable.sol, like this. Now we can make our minimal account iAccount and ownable. And since we're making this ownable, we have to add a constructor ownable, and the initial owner is going to be message.sender, like this. Cool. So now that we have an owner of this smart contract, we're going to set this up that whoever is the owner of this contract is going to be the one to validate the transactions. And so actually, I guess this is kind of cool because you can transfer ownership of this smart contract wallet to different wallets. And so I guess that is actually kind of cool. That is a bit of a novel feature. So you can transfer ownership of a wallet without ever having to share your private key. You know what? Actually, I take it back. That's cool as hell. So let's actually go ahead. Let's create a function called _validate signature. And we're going to take the user operation and the user operation hash. And we're going to use these to actually validate the signature. Because remember, the user operation is going to be basically all the stuff, the meat of like, hey, what's the transaction that we're trying to even send? And then the user operation hash is going to be the hash of all this stuff. So we want to make sure that this signature that they're sending us is a valid signature for the hash of all this stuff, right? So this owner, this message.sender, the owner of this contract should be the one to sign all of this, populate that here, and then we can check via the hash and then via the signature that stuff looks good. You'll understand what I mean in a second. So cool. Let's create the function. So we'll say function underscore validate signature. And this is going to take the packed user operation. I think we can keep it as call data, bytes 32 user OP hash. We'll have this be internal view. And we're going to have this actually return a IEntry256 validation data. And you'll see why we need that in a little bit. So this is the function that the IEntryPoint contract is going to be calling, right? Validate user operation or validate user OP. And they're going to populate all this stuff here. And this user OP hash is going to be the EIP 191 version of the signed hash. So this is technically in the wrong format. And I'm not going to go on kind of a side tangent on what these EIP 191 hashes look like. My co-instructor Kira is actually going to go over that a little bit in another video. So hopefully by now you actually know what those are. But they're going to send us this hash, and we actually need to convert this hash back into just like a normal hash. And OpenZeppelin actually has a tool for us to do that as well. So I'm going to import that, import message hash utils from at OpenZeppelin /contracts/utils/ cryptography / message hash utils.sol. And if we look in here, let me comment this down so I can look in here. If we look in here, there's a function called toEth signed message hash. And this is actually the function that we're going to be using. It's going to return the Kachak 256 digest of an EIP 191 signed data with version 0x45 or the personal sign message. So I know there's a lot there, but we need to basically format this hash into the correct format here so that we can do an ECDSA recover, which is going to give us who actually signed a hash. So a little bit of a pre-processing step, if you will. So we're going to say, we're going to get the hash. We're going to say bytes 32 ETH signed message hash equals message hash utils dot toEth signed message hash user OP hash, like this. And now that we've converted this user operation hash into kind of this correct format, now we can do this thing called an ECDSA recover. So we're actually going to grab some tools for that as well. Import ECDSA from at OpenZeppelin /contracts /utils /cryptography /ECDSA.sol. I feel like most of the time in smart contract development, we never have to deal with signatures or any of this stuff. It's just when we're doing accounts that we do. So we're going to be calling this function recover. And what this does, it does try recover, gets the RS and V, calls try recover again. And we eventually call this precompile called EC recover, which basically says, okay, this is some signed data. Here is the hash. Here is the signature. Who actually did the signing here? And if it's valid, the math will all check out and it will return a correct address. Otherwise, it'll return address 0 if it's wrong. So now that we have this set up correctly, and I know there's a whole bunch of math here, don't worry, Kira's going to come out with a video that's going to be phenomenal if none of this makes sense to you. If you're watching this on YouTube, link in the description. If you're watching this on Cypher and Updraft, you should have just watched that. So go back and watch it again if it doesn't make sense quite yet. So we have this in the right format now. Now we're going to actually get the owner. So we're going to call ECDSA.recover. We're going to say ETH signed message hash user OP.signature. So we're going to say, okay, with this signature and with this data in this hash, who signed it, right? So we're going to say address signer equals this. So ECDSA.recover is going to return who actually did this signing. And then all we have to do is we can say if signer does not equal the owner, then we're going to return sig validation failed. Otherwise, we're going to return sig validation success. So this sig validation failed and this sig validation success. Failed is just 1 and success is 0, but we don't like magic numbers, so we're going to set it up like this. We could 100% say, failed and success up at the top, but I kind of want to follow the same patterns as the account abstraction playbook. And so what we can actually do is they have these defined in a group of helper contracts. So we're actually going to import those. So we're going to import sig validation failed and sig validation success from lib/account abstraction/contracts/core/helpers.sol. Like this. If we look up this helpers.sol contract, we can see sig validation failed equals 1, sig validation success equals 0. So we're just going to follow their standard. So if it failed, return it failed. Otherwise, return successful here. So all we're doing is we're saying, given kind of this hash and the signature that they gave us, let's verify the signature is the owner of this contract, right? Is the owner, because that's the only signature validation here. But this is where we would say, all right, make sure that the Google session key is correct. Or make sure that 7 of your friends are signing this, or make sure that this or that or the other thing, right? So this is where we get to do a lot of that cool stuff. There's additionally a signatures aggregator, which we're not going to get into, but we can do more customization with that. So anyways, so back in our validate user op, we can now say uint256 validation data equals validate signature. And if we go back to our iAccount, let's grab this, go back to our iAccount. We have this return validation data. This is the packed validation data structure. Basically, the first 20 bytes is going to be 0 for a valid signature or 1 to mark signature failure. And that's actually why we're following this process here. There's also some really cool additional pieces you can have. You can have valid until, valid after for a time range. You can do some other cool stuff here. But for us, we just need to make sure we return the uint256 validation data. And for us, our validation data, we've already got it defined right here. For us, if it failed, it's going to be 1, so we should fail. And if it's going to be 0, we pass, hooray. We're not quite done yet. Ideally, we would also want to validate the nonce. So in this packed user operation data, there should be a nonce. We could keep track of like the nonce in here. So we could do like uint256 our nonce equals 0. And we could have some validation on the nonce. We could say, hey, it needs to be sequential, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You need to do in order. You need to do any order. It's going to be in a mapping. It's going to be this, that. You could do whatever we wanted here. But the actual nonce uniqueness is managed by the entry point itself. So we don't really have to do anything ourselves here. So I'm just going to comment this out and not do anything. But ideally, you should do some type of nonce validation. And then finally, we also have to pay back money to the entry point. So this missing account funds bit is basically going to be, hey, here's how much this transaction is going to cost, and here's how much you need to pay back to whoever sent the transaction. If you have a paymaster, you can add on into this to have the paymaster actually do the payments. However, we're not going to deal with any of that. So we need to have a little pay pre-fund transaction or pay pre-fund function where we actually pay the entry point contract the amount it's owed. So we'll do a little function pay pre-fund uint256 missing account funds. We'll have this be internal. And we'll say if missing account funds is greater, or I guess not equal to 0 or greater than 0, then we'll do a classic, bool success, comma, equals payable message.sender call value missing account funds. Gas is going to be type uint256.max and then no data and then success. So we're just going to say, hey, pay back the entry point contract. I guess hypothetically we should hard code this to be the entry point contract, but it's the entry point's job to verify the payment is good, not us. So we don't really need to care about this at all. So we can even just do this. but we're probably going to get yelled at by our linters, so whatever. So we just need to pay back the entry point contract. And speaking of which, we should really have this validate user OP only be callable by the entry point, but we'll add that in a second. So at a high level though, this is really all we need. This is kind of all the functionality that we need. This is kind of all the functionality that we need to have a valid account abstraction based account. Now, at the moment, anybody can validate user operations through this, which isn't great. And anybody can basically pay themselves, which isn't great. So we probably want to lock this down. Let's do that, shall we? But this is already awesome. Like you've already essentially created your own minimalist account for Ethereum or any EVM chain that doesn't have built-in account abstraction. Great work. So let's keep going on this though. So we're probably going to want to make sure that this validate user op is only callable by that entry point contract. So right in our constructor, we'll do a little address entry point like this. We'll create a state variable called address I underscore entry point, make this address immutable, private, of course. And then we'll just say IEntryPoint equals entry point. Now I am going to go one step further though. I'm going to go ahead and import the IEntryPoint interface, and then that will actually tell us more about how the entry point actually works. And it'll allow us to add some nice getter functions to this as well. So I'm going to do a little import IEntryPoint. So the IEntryPoint interface from lib/account abstraction /contracts/interfaces/IEntryPoint.sol. And if we look in here, we can see kind of all the different functions the entry point interface, the entry point contract can work with. The biggest one being obviously handle ops, but they've also got some other nice ones like get nonce, where it can get the actual nonce or increment nonce of a smart contract wallet. So in any case, I'm going to have, instead of this being an address, I'm going to have this be an IEntryPoint, and we're just going to wrap this like this. I'm going to do some little headers, getters like that, so that at the bottom, I'll add this in, I'll do a little function get entry point. Looks like GitHub Copilot got me here. And if you don't have that headers tool, definitely be sure to check out Transmissions 11 headers tool for making beautiful headers like this every single time. So we'll do headers, getters like that. And cool. And then we have a little state variable here. Looking good. Okay, cool. Now that we have this, we should probably create a modifier called require from entry point like this. And then we'll do if message.sender does not equal address I underscore entry point. Then we should revert with some new custom error. I'm going to call it error minimal account not from entry point like this. And so we will revert this and boom. Now that we have this modifier, we can make our validate user operation exclusively from the entry point here. Cool. All right, great. So now are we done with this? This is looking really, really good here. Are we done with this? Not quite. We're actually just missing one final thing here. So here's what's going to happen. So remember, this minimal account is going to pretend to be our EOA, right? This is our account abstraction account. This contract needs to be able to do stuff. Right now, if we send a transaction, we can go ahead and validate this, right? But again, if we look at our little image again, we need to remember that our account, well, actually, this isn't a great image. Let me go use the other image. Our minimal account contract needs to be able to call and interact with all the dApps that we're going to be working with here. And as of right now, this contract can validate user operations, but it can't actually send any transactions itself. As of right now, it's not possible for this contract to actually send a transaction, like to Aave, for example. So we actually need to give it the functionality to do that. So the entry point, right, if we go back to this image, the entry point is going to validate a transaction on our account, and then it's going to pass the transaction information to our account, and then our account will be the message.sender and actually send and interact with the dApp or whatever, right? So we need to add probably one of the more important functions here, a function called execute. And we'll add this up here. I'm actually going to go ahead and make a couple of headers. Headers internal functions like this. I'm going to put this like here. Headers external functions like that. We're going to do, oh, I put that in the wrong spot. Whoops. So external functions, internal functions. And then we probably would want to flesh out our NAT spec, but I'm not gonna do that right now. Okay, cool. So we're going to need to add a new external function called execute. And this is going to be the function that whenever we send a user operation to the entry point, we're going to say, hey, you're going to need to call that execute function on our contract to call the dApp. So a little bit confusing from our end as developers, but this will make the lives of the people who are using these account abstraction accounts much, much easier. So we're going to make this execute function, and we probably want to add the things in here that are needed to execute a function, right? So we're going to need an address dest for the destination, a uint256 value if they want to send any ETH, and then a bytes call data, function data or func data, or just, yeah, function data, where this is going to be the ABI encoded function data, right? And this will be external. And we could have this as exclusively require from IEntryPoint, where only the IEntryPoint can call this. And that would allow this setup to work great, where IEntryPoint calls our account and then our account calls the dApp. But this would mean that our MetaMask has to go through kind of this long account abstraction process every single time. And maybe it makes sense for them just to call straight from their MetaMask directly to the account if they want. So we're actually going to make an additional modifier here called modifier require from IEntryPoint or owner, where the owner of this minimal account can also call our smart contract account, or it can be the entry point, right? So either one, we're happy for both ways. And the reason we're happy for both ways is because if the owner is calling, then that's obviously proof that the correct person is actually calling this. However, if the entry point is calling this, right, it's when the entry point is going to call validate user operation, and all the signatures are going to have to be validated here. So cool. So require from entry point or owner. This will be our modifier. We'll say if the message.sender does not equal address I_entry_point and message.sender does not equal owner, then we're going to revert minimal account __ not from entry point or owner. Like this, little underscore here, and then we'll create this new error, paste that in here. Cool. And then I just kind of want to be a little bit more explicit here. So I'm going to do some more headers, errors, because I love me a good, nice, clean code base. We'll do headers, state variables, right? And state variables could be storage or not storage. We'll do headers, modifiers, this, post that in there, modifier, and then headers, functions. And then just paste that here. Just kick it off with the constructor, external functions, internal functions, getters. Okay, cool. I love me some clean headers. Mwah, the code base is starting to look cleaner and cleaner. Obviously, we'd want to add some NAT spec in here to make this look even cleaner, but oh, the headers just make it look so nice. Okay, beautiful code is good code, friends. Okay, so now we have this execute function, and we would definitely want to add some NAT spec onto this, but I'm going to skip it for now. We would definitely want to add some NAT spec onto this, but all we're going to do is just a basic low-level call for this execute function. So we're going to, in here, we're going to say, okay, a little bool success, comma, bytes memory result equals dest.call, value will be value, and then the function data will be here. We'll say if not success, then we can go ahead and do a little revert here. And then we'll do a little revert, minimal account, just say call failed. We'll even pass the result as part of the failure reason. And that means way back up here, we'll do a little error, minimal account, call failed, bytes in here. So we'll actually revert with whatever the return data was here. And that's looking pretty good. All right. And then the last and final thing here we need to do is we need to add a receive function, external payable, because this contract needs to be able to accept funds in order to pay for transactions, right? Because again, we don't have a paymaster. So whenever the alt mempool sends a transaction, it's going to pull the funds from here, which we pay them in our, where is it? In the pay pre-fund down here. So our smart contract needs to be able to accept funds, first of all. So now people can directly call through this alt mempool to the entry point to our smart contract, or they can just call it directly into our account if they're the private key owner of this. Okay, cool. And with just this, we can actually go ahead and write some scripts to test this, deploy this, and have this be our minimal account. Awesome. This is incredibly exciting. Let's keep going. So now, as many of you know, let's go ahead and write some deploy scripts here. We'll call deploy minimal.s.sol. We're probably going to need a helper config.s.sol because oops, this should not be a folder. Delete that folder, change it to a new file. We're going to need a helper config because the entry point contract is going to be different on different chains. So we're going to need to interact with that contract here. And then additionally, we're going to create a send packed user op.s.sol. And this is going to kind of be the pinnacle of what we're looking to do here, this send packed user op.s.sol. So, and if everything works here, this should also work marvelously. Yes? Yes. Okay, cool. And it's in us writing this where actually the blunt of our work is going to be, because we're going to have to understand how all the signing and the creating of the data works. And this is really where the complicated nature of this kind of comes into play. So, but let's go ahead and let's learn how to deploy this real quick. The deploying is pretty easy. So we'll do a little pragma here. MIT 0.8, I think we're using 24 here. And to get this going, this is going to be a script. So we're going to do import script from forge std/script.sol contract deploy minimal is script like this. We have to import our minimal account from sc/ethereum/minimal account.sol. Oh, is that wrong? Do a little forge build to make sure everything works. And it looks like everything isn't working. .toml open zeppelin/contracts equals lib. Open zeppelin contracts /contracts. Let's try that. Okay, there we go. There's some other issues here. That's not found. Import minimal account. Oops. Contract minimal account. What's it mad about? Try forge build now. Okay, minimal account. Okay, cool. And those just don't have a compiler version. Okay, great. So now that we have those, we're going to, of course, need to make a function run. And we're probably going to need to make a function deploy minimal account. Public that we're going to call in run. So for our minimal account, all we need is an entry point. And we should definitely do that in a helper config. So let's go to our helper config here. Let's get this set up. A little pragma here, MIT 0.8.24 contract helper config is script like this, which means we're gonna have to import script from forge std/script sol like this. We're going to create a little error. Helper config __ invalid chain ID. I should probably just turn this into a package, this helper config, and then you in the Foundry DevOps tool maybe. But we're gonna do a little struct network config. This is going to have an address entry point like so. Then we'll do, where are we going to deploy this? So we'll say UN256 constant ETH Sepolia or Sepolia ETH Sepolia chain ID equals 1115511, I think, ETH Sepolia. And then we'll do UN256 constant zk sync sepolia chain ID equals 300, like so. And I'm just gonna paste this here for now so don't forget it. We'll create a little network config, public local network config. Yeah, I should definitely turn this into a package. Sorry, I haven't turned this into a package yet. And then we'll do a mapping uint256 chain ID to the network config, public network configs. I'll do a little constructor network configs of ETH Polia chain ID is going to equal get ETH Sepolia config. And let's go ahead and create that function. Get ETH Sepolia config, public pure returns network config memory, like this. And we'll say return network config entry point. It's going to be this address here. A lot of boilerplate stuff we get to do, and I'm just going to copy paste this for zk sync. Get zk sync Sepolia config. For zk sync, since it has native account abstraction, we're going to do address 0, which again I haven't taught us about that yet, so you can kind of just ignore that for now. But we also want to do function get or create anvil ETH config, public returns network config memory, like this. We're going to say if local network config dot entry point does not equal address 0, then return local network config, like this. Or we'll probably have to come up with something a little bit more clever because this is also going to return 0. Otherwise, we're going to have to deploy a mock entry point contract. And we'll do that a little bit later. So let's just add another function. Function get config by chain ID, uint256 chain ID, public view returns network config memory if chain block, or excuse me, chain ID, or actually, excuse me, function get config, public view returns network config memory, get config by chain ID, block dot chain ID. All right, uint256 constant local chain ID equals 31337. This. If chain ID equals this, then we're going to go ahead and return get or create, like this. Else return else if, we're going to do this conditional again, if network config of chain ID dot entry point does not equal address 0, then return like this, else revert with this error here. And that means this can't be a public view, it just has to be public. Cool, this can't be public view either because we have this. Okay, cool, and then we'll deploy mocks down here in a little bit, but cool. So now we can get the config just by calling get config, which means back in our, oh, whoops, I put this in the wrong one. Let's put this over in the right one here, which means back over here, I can import helper config from script / helper config.s.sol. In our deploy, we can say helper config equals new helper config. We can say helper config.network config equals helper config.get config, like this, memory. Now we can just do a minimal vm.start broadcast, vm.stop broadcast, like this. Probably want to set up an account in here, but I'm not going to bother. We can just say minimal account equals new minimal account. And then I'll do minimal account dot transfer ownership to message dot sender. So this should pretty much already be the case, but just to make sure our tests are all working correctly, I'm just going to do this. Oh, and this is actually going to be fig.entryPoint in here. Ta-da! It's a little Forge build. Make sure everything's working. It sure is. Okay, very nice. Now we're probably going to want to add an account in here as well. So I'm actually just going to go back to our helper config. Up in here, create a little address account like this. I'm going to create a constant. I'm going to say address constant burner wallet, because if I interact with this, I'm definitely going to want to use a burner wallet. I'm going to grab my burner wallet address here. Then in here, we're going to do, for Sepolia, we'll do account. This will be the burner wallet, or this should really be your testnet wallet, but burner wallet works fine too. And then we'll do account burner wallet like this. Cool. And then instead of entry point does not equal larger 0, let's do account, because down here we're actually going to use address 0 for like real. So we'll do, instead of entry point, we'll do account does not equal address 0, and looks much better. Okay, cool. Now we're going to deploy the mock entry point in a little bit, but fig.account, but I want to just get this all set up here, and I want to get a basic test going. Okay, cool. So we now have a deploy script, actually, oops, returns helper config memory and minimal account like this. I'm going to do return helper config and minimal account. Oops, sorry, nope, just straight up helper config. Okay, cool. So now we can use this in our test. We can go over to tests, create a new folder, Ethereum, and then here, minimal account, test.t.sol. And let's start building a test for this. And this test is actually going to be kind of bonkers in a good way. We're going to do a lot of signing of stuff. We're going to do a lot of API encoding of stuff, and we're going to be learning a lot during this. So buckle in, because this is where it gets fun. Okay, MIT 0.8.24. Is that what we're using? 0.8.24, yep, okay. Contract minimal account test is test like this. Import test from forge std/test.sol. All right, great. Function set up. You know the drill here. You've done this 100 times. We're gonna need to import that minimal account from src/ethereum/minimal account.sol. We're gonna need to import deploy minimal. Is that the name of it? Deploy minimal from script/deploy minimal.s.sol like this. And we're gonna do in here, deploy minimal equals new deploy minimal dot, what do we call it? Deploy minimal account, deploy minimal account. And we're going to get the helper config back. So we're going to say import helper config from script/helper config.s.sol like this. And we'll say helper config and minimal account equals deploy minimal account, deploy minimal account. And what's it meant about? Deploy minimal account, helper config, minimal account. Oops, that's because I spelled it wrong. Okay. And you know what? Let's actually make these state variables. And let me do a little word wrap here. Config, minimal account, get rid of this and get rid of this. Ta-da. All right, we are cooking. So now what do we want to test? So we basically want to test that somebody can sign the data, go through this alt mempool, go through the entry point, and then have our contract do something. We could have it do really anything, but I kind of want to test working with a contract. So for us, our test is going to be a USDC approval, right? So the message.sender should be our minimal account, and it should approve some amount, the USDC contract, but it should come from the entry point. Because if we work this in such a way that it actually works if it comes to the entry point, that means all these alt mempool nodes will be able to bundle our transactions. They will be the ones to submit it, and all this stuff will be peachy hunky dory, right? So we're going to go ahead and write some tests to kind of simulate bundling these transactions, sending this transaction. We are essentially going to simulate being these alt mempool nodes here. So this is going to be really exciting for us to do. So let's start writing some tests, and we're going to have to update our setup and update a bunch of stuff in here, but let's keep cracking. So let's do a quick little function just to see if our basic functionality works, right? So this execute function that we created, where is it? Execute. The owner should be able to call it and like send a transaction through here, no problem. So we want to make sure that this flow works, right? So before we even get to the account abstraction stuff, we just want to make sure that our off-chain private key, our off-chain owner can call the minimal account, which can call the USDC directly, right? Because this is kind of going to be the simplest flow. And this will give our user, our minimal account users, kind of the most customization with this minimal account, right? Because they will be able to then directly interact with this contract or send the transactions to the bundlers with the alt mempool stuff. So let's just test to see if directly calling this works. So we'll do a little function test. Owner can execute commands, be public, and minimal accounts up there. So let's do a little arrange, act, assert going on here. So for arrange, what should we do? Well, we should probably get a mock ERC20, right? So let's go ahead and get that. This actually comes directly with Foundry and OpenZeppelin. So we're going to use the OpenZeppelin one. So we'll do a little import mock ERC20 from at OpenZeppelin/contracts/ I think it's mocks / ERC or mock ERC or what is it? ERC20 mock.sol? Is that what I just looked up? ERC20 mock. ERC20 mock, yes. Contracts mocks token. Contracts mocks token. There we go. And it has mint and burn. Great. Open Zeppelin contracts mocks token. ERC20 mock. Okay, cool. And then we'll do a little ERC20 mock, USDC. We'll say USDC equals new ERC20 mock. And the ERC20 mock takes nothing. Okay, cool. So we're going to do a little USDC approval. Actually, we can do a little USDC mint. Let's do a little USDC mint. Take it back because in this mock, we have this mint function. Let's just test that. That's a little bit easier and more fun to test. So we can kind of start by assert equal the USDC dot balance of address minimal account is going to be 0 like that. Then we could say address destination is going to be the address of USDC, right? Because what are we testing in minimal account? We're testing execute. So we're going to need destination value function data. So our destination is going to be our USDC contract. Value is going to be 0. And the function data is going to be the mint function. So dest is going to be this. U256 value is going to be 0. And then we can do bytes memory function data equals. This is where we do some wonderful ABI.encode with selector ERC20 mock.mint.selector like this. And if you're not familiar with how this works, definitely be sure to go way back to the NFT section to learn about this, the NFT section of Cypher Updraft. So this is going to get us the function selector of this. We actually could also just do this, actually, now that I'm thinking about it. But I'm going to do this for verbosity, because if this did have parameters, we would, add the parameters in here. But in any case, so now we need to prank the owner of this. So we can do a little vm.prank minimal account.owner like this. And then we can run minimal account.execute dest value function data. And this should have our minimal account mint some ERC20 mock to the minimal account, right? So, and let's do assert equal USDC dot balance of address minimal account should be, how much are we minting here? Let's go back to that ERC20 mock. Mint, excuse me. Mint does take an amount here. So let's actually go back over here. Let's go up to the top and we'll do UN256 constant amount equals 1E18 amount. So what did we just say it was? It was going to be account and amount. So we want to do, when we encode this, we want to do the account. So we'll say address minimal account and then the amount like this. And now we're actually encoding mint with minimal account and amount. So this is actually kind of a more fun test because we're testing a function with parameters. So I like that a lot better. So USDC.balance of minimal account should equal this amount that we just added in here. And great, that's our whole test. Let's give this a whirl. Forge test --mt, paste this in. Let's add a couple of V's. Let's zoom in a little bit. Setup failed, invalid owner. It's because passing in the 0 address. So when we do our deploy minimal account here, this account.config, if we go over to the helper config, we don't have this set up, so it's giving the 0 address. So yeah, let's go ahead and set this up here. So let's do return network config entry point. Let's just do address 0 for now, because we're going to need to create the mock in a minute, but for now, let's just do address 0, and then we'll do account. I'm going to cheat a little bit, and I'm going to use the Foundry default sender for this. So if you look in base.sol, we've mentioned this a few times before, the default sender for Foundry is this kind of default caller. It's this address right here. So I'm going to use this here. Up at the top, I'm going to say address constant Foundry default wallet equals that address here. And we're going to have the account be the Foundry default wallet like this. So it can be restricted to view, and then we'll deploy mocks in a little bit. But okay, so now we actually have an account here, the Foundry default wallet. So now if we rerun this test again, this one should actually work now that we have a non-zero address sender, not from EntryPoint. Oh, let's go to our minimal account.sol. Require from EntryPoint. Require from EntryPoint owner. This is why we write tests, my friends. So let's run that again. And boom. Okay, cool. And it's giving us a warning because we haven't finished this function yet, but we have this passing. And this is very exciting because now we know for our minimal account abstraction, we can at least do this setup right here, right? Cool. Now we want to move over to make it do this setup. And there's going to be a couple of steps that we're going to do to get there. All right, cool. Well, we should probably do one more. We should test that. If you're not the owner and you're not the entry point, you should not be able to do commands. So we'll do a little function test non-owner cannot execute commands public like this. Arrange will be pretty much the same as what's up here. So actually just going to grab all of this. Yeah, I'm just going to grab the whole thing. And instead of minimal account.owner, we're going to do a little random user address random user equals make a DDR random user like this. And then back down here, we will do a little vm.prank random user forge test, and we'll have everything compile here and run. Oh, duh. It failed successfully, but I forgot to tell it it's going to fail. So we'll do a little vm.expect revert, and this will be minimal account.minimal account __ not from entry point or owner.selector. Rerun the forge test. And voila. Okay. Things are looking good. Now we get to go into the fun stuff. We just tested the execute, which is cool. We need to test this validate user operation. So in order for us to test this, we're going to have to create a packed user operation. We're going to have to get the hash of it, and we're going to have to figure out how much it costs. I think we can skip a lot of that though. And we're probably going to have to refactor some of our tests so we can work with keys to actually do some of the signing here. And kind of our ultimate goal is going to be function test validation of user ops like this. This will kind of be our final test, but before we get that, we should probably test a couple of other things first. So in this validate user OP, the first thing is going to be this packed user operation, right? Which we can get from this contract here. And it's going to be this struct and it's going to be this signature. So we are actually going to have to write a script here that actually can generate all this code, all of this, and then actually sign it. So we could do this 100% right in our tests here. However, when we send a packed user operation, we're going to have to sign it anyways. So we might as well just actually create the code in here and then reuse it in our tests, because that's going to be much better, because then we'll get to test actually our signatures over here, test our signature creators inside of our tests. So before we can even test validation of user ops, we're actually going to have to test creating this packed user op, right? So we're actually going to have to test creating this packed user operation. So we're going to have to make a script that will add all of this stuff in, that will sign this, and then we need to make sure that this packed user operation is good and that the signature that we used is good as well. So, and then only then can we actually run this. So we have to take a step back and let's start writing this send packed user operation. And this is actually what we're going to do to test on an actual testnet or an actual mainnet. I tested this on an actual mainnet because I wanted to see the real experience, but you don't have to do that, of course. So we're actually going to build it here so that we can work with everything. Make sense? Okay, great. Let's jump in. Okay, so you know the drill, pragma, like this MIT 0.8.24 contract send packed user op is script. That means we're going to have to import script from forge std/script.sol like this. We're going to have a function run public, which we're not going to define yet. Then we're going to have a function called generate user operation like this. And this is what we're going to have to build here, this get signed or generate signed user operation. And this should return that exact thing that we're going to pass to our minimal account here, right? We're going to have to pass this packed user operation type. So we're going to want to import that. So we're going to say import this packed user operation from, and this is actually in the lib account abstraction, /contract/interfaces/packed user operation.sol like this. And this is going to return this packed user operation, and this is a struct, so packed user operation memory like this. And here's where we get to use all the fun signature knowledge that we've recently learned to actually generate this signed user operation. So first, we're gonna have to generate the unsigned data, and then we're gonna have to sign it and return it like this. So let's actually focus on this first generate unsigned data, and I'm actually going to put this in a separate function. So I'm going to have another function here, function called _generate unsigned user operation like this. And this is just going to take some bytes memory called data. We'll have this be internal pure, and it should return also a packed user operation memory, except this one is just not going to have the signature. Right, so if we go back to this file, this is the packed user operation. So our generate unsigned user operation is just going to populate all these fields basically, leave the signature blank, And then we'll have this generate signed user operation actually do the signatures. So this will definitely be the easier one. So let's even just get started here. We'll do a little return packed user operation, and we'll just populate the fields as we see fit. So the first is going to be a sender, and we probably need to pass that in as a parameter as well. So we'll do address sender like this. Sender will be sender. We'll do a little nonce. This is where we probably want to be clever with our nonce here as well. We'll probably want to parameterize that too. So we'll do nonce or uint256, right? It's a uint256. Yep, uint256 nonce. We'll say nonce is nonce. Init code. We probably could modularize this as well, but we're going to ignore this, right? Because we're not going to be initializing any contract. So we're just going to do a little blank data bit here. Or do I do hex? Hex like this. Yeah, okay. Then the call data is just going to be the call data. And the call data, of course, is going to have, all of our function data to call. All right, next is going to be a couple of different gas limits. Now, I'm just going to kind of wing this. We don't really need to get this exactly correct because a lot of these are just limits here. So just roll with me on these. So account gas limits, we're actually going to make a couple of different variables at the top. We're going to do a uint 128 verification gas limit. This code was inspired by some of the ideology that was used to build some of this account abstraction bits here. So this verification gas limit, we're just going to say 16,777,216. And just know that this is probably going to be fine. If you run into issues with gas, you might want to tweak these a little bit, but this is what we're going to run with for now. Uint 128 call gas limit is going to equal this. So these are going to actually be the same. And then for the account gas limits, we're going to do some clever ways to concat these two variables together, even though they're kind of the same thing. So bytes 32, uint256, verification gas limit. And if you don't understand exactly how this is working, don't worry too much about it. A little left shift 128 gas limit like this. So this is really just kind of us combining these two into one bytes 32. If you want to jump into Chisel and play with exactly what this will return, you are more than welcome to do so. But then we're going to do pre-verification gas is just going to be this verification gas limit. Then we're going to do gas fees like this. And we're going to have to make some more clever stuff here. Again, this is where we could be clever with how we're doing some of the gas fee stuff, but I'm going to say max party fee per gas is going to be 256. This, and for gas fees, we're going to do a little concatenation as well. Bytes 32, uint256, max party gas fees, shifted 128, or max fee per gas, which we're going to have to create that as well. We say uint 128 max fee per gas equals max party gas fees. Yeah, like I said, if the gas fees don't quite make sense here, don't worry too much about it. They're just gas fees and gas limits. Then what we have paymaster and data. We did not add a paymaster. So paymaster and data, we're just going to say hex blank. We're going to pass nothing. And then for signature, we're also just going to pass some nothing here. Okay, cool. The reason I put this in its own function is because this can be kind of gross here. But we have our generate unsigned user operation, which just generates essentially just this struct for us. So what we can do now is we can say packed user operation unsigned user op equals generate unsigned user operation. This will take the bytes call data or bytes memory call data. Excuse me. This needs to be bytes memory call data address sender. And we're not going to pass the nonce in here because we're actually just going to use a Foundry cheat code to get the nonce of the sender. So there's a get nonce address account, get the nonce of the given account or wallet. Boom. We can just do it like this. So we'll do a little uint256 nonce equals vm.get nonce. sender like this. And then we'll pass the call data in here, the sender in here, and then the nonce in here as well. And this, of course, needs to be memory like this. Okay, nice. Great. Now we have this unsigned user operation. Now let's just go ahead and sign it and then return it. So, okay, great. So we have this packed user operation. We just don't have the signature. We just got to sign all this. Now, in order for us to actually sign this, we have to get the user operation hash that the entry point contract is looking for. So we want to actually sign this the way that the entry point contract is expecting. Now, if we go back into our lib account abstraction, I'm actually just going to cheat a little bit and look for the entryPoint.sol right here in account abstraction. There's actually a function in here called getUserOpHash. And this is how our entry point contract is expecting that hash to be created. So what we could do is we could 100% copy paste this, or we could kind of take this time to actually deploy our mock entry point contract and then use this getUserOpHash function to actually get the user OP hash. So, and what's important to know is that the chain ID is going to be part of the user OP hash. And this is actually really important so that we don't have cross-chain replay attacks. It's also hashed with the actual entry point address, so there's no issues with using different entry points. And we want to use whatever function the entry point contract that we're actually working with is using. So back in our helper config, we're going to need to add that entry point contract address for Sepolia. Well, not for zkSync, but at least with our Anvil, our local, we want to deploy a mock entry point contract so that we can actually work with that when working on our local network. So let's go ahead. Let's actually import that entry point contract. We'll do a little import entry point from lib/account abstraction/contracts. Where is this? Contracts core/entry point.sol, like this. And then down in our mocks, we can actually deploy this. I'm also going to grab a little console here, console2 from our script. I'll do a little console2.log, deploying mocks, ... Then we'll do entry point equals new entry point like this. There's no constructor or anything. And then we can take this entry point address here and boom, do address entry point like so. And then we're also going to want to do vm.start broadcast of the Founder DeFi wallet, just in case we're on Anvil, and then vm.stop broadcast, of course, like so. Nice. So now that even our local one is going to have this entry point contract here, we can use it to call that getUserOpHash function. So we're actually not going to assign it quite yet. We're actually going to get the user OP hash, and then we're going to sign it. And then we're going to have to do some clever signature stuff to actually sign it. So to get the user OP hash, we're going to say bytes32 user OP hash equals, and this is where we're going to have to get past that helper config address. So in another parameter here, we're going to get that config. So helper config.network config. To import that as well. Import, or actually we can just do network config from script/helper config.s.sol. We don't even need helper config. We can just import that network config like this. And actually, if we do this, we don't even need the sender, because instead of doing the sender, we can just say config.account here, and we can do that here, config.account, like there. And then the user OP hash is going to be config dot like this. We're going to need to wrap this in an IEntryPoint interface. So import IEntryPoint, and you can see why we installed this as a dependency here. Import IEntryPoint from lib/account abstraction/contracts/interfaces/IEntryPoint.sol. So we can do IEntryPoint config.entryPoint dot get user OP hash and pass in our unsigned user OP right there. Cool. Then once we have the hash, we can convert this into an ETH signed message hash. So there's actually a function called toEth signed message hash that takes a bytes 32, and this is going to return the Kachak 256 digest of an EIP 191 signed data with version. Oh, so we're basically just going to add all this EIP 191 stuff to our bytes 32 so that it turns into a proper digest for signature stuff. So we'll do a little bytes 32 digest equals this user OP hash dot toEth signed message hash, signed message hash. And since we're putting this function onto our bytes 32, we're going to have to import that. Oh, it looks like we're having an issue. We probably are going to have to do the helper config, but let's go ahead. Let's do import message hash utils from @open zeppelin /contracts /utils /cryptography /message hash utils dot so. And then we're going to say using message hash utils for bytes 32. And it looks like this is actually causing issues. So let's just do helper config dot network config like that. Okay, cool. We'll run a forge build in a minute. So, okay, so now we have the digest. This is the correctly formatted hash. So we're pretty much on the home stretch. Now, all we need to do is sign this digest here. So we're going to do a little vm.sign. We're going to have the private key, comma, digest here. Now, here's one of the cool things that you can do in Foundry. Typically, this is where you'd have to do a vm.env uint private key, whatever. You'd have to stick your private key in here. But as you know, because you're taking Cypher and Updraft, yeah, you don't do that, because that's a great way to accidentally expose your private key. So we're not going to do that here. So Foundry is pretty clever, where if you have unlocked a key, right? You know how in Cypher and Updraft we teach you to do, forge script -- account instead of -- private key. Well, if you have a private key unlocked with an account, you can just do config.account. You can basically pass this an address, and Foundry will be smart enough to go, okay, so we're using an address here. Let me check if I have that key unlocked. I sure does. Boom. We're going to use that unlocked private key to actually sign this, which is outstanding. So we're actually going to sign this. And if you watched Kira's video, we're going to get that uint 8v, that bytes 32r, oops, bytes 32r, where is that? Bytes 32r and the bytes 32s, like this, from the signature. And then we're finally going to create this signature at the bottom by just combining these values together. So we're going to say user signed operation equals, excuse me, we're going to say user signed operation dot signature equals ABI dot encode packed R, S, and V. And just be sure to note the order. This is VRS and this is RSV. I must have spent like 3 hours trying to figure out why my signature was wrong, and it's because I had the order wrong. So note the order here. And then we're going to return our unsigned user operation. Actually, this is kind of confusing because now that's signed. Let's just rename this to user op. Okay. So we now have a function called generate signed user operation. It's probably giving me a warning because this should be view. Let's call this a view. Generate signed user operation. We have generate unsigned user operation. And we can now use these in our tests. And we're passing call data and a config. So what we're going to do now is we're going to pop back over to our test now that we have a script to actually do this. Way up at the top, we're going to do send user operation, send packed user operation. Send packed user op is going to be a state variable that we'll use. We're going to go ahead and import it. Send packed user op from script / send packed user op .s.sol, like this. Send packed user op, send packed user op. And then now what we can finally do is we can finally test that this actually works. So before we actually test the validation of our user op, let's just test that we're actually signing stuff correctly, right? Because If we're not signing stuff correctly, then our validation isn't going to work correctly either. So let's create a little function here, a little test function called test recover signed OP. And this will be a little public view function. And this is where we're just going to do an ECR recover on our signed user operation hash. And if we get the correct owner, this should work well. And I'm going to do a little refresher on all this. We're going to kind of summarize what we learned after we write this test, because I know we've gone over a lot of stuff. Don't worry, you're doing phenomenal by getting this far. And we're going to go over this again. So don't worry too much. So test recover signed operation. Let's do a little arrange act assert here for our arrange. We're actually going to cheat a little bit. We're going to copy all this because we're going to do the exact same arrange here. And we also need the function data as well. And now we're actually going to combine all of this into the execution call data. So when we did the test above here, we only need the function data because we were just calling directly this execute, right? And this execute will call the USDC and pass the, the function selector and all the data that needs to go to the USDC. What we need to do, because we're planning on having validate user operation work correctly, so we are actually going to have to code our call data that tells the EntryPoint contract to call our contract and then have our contract call the USDC. So we've encoded this bit here, but we also now need to encode first calling the EntryPoint and then calling the minimal account, right? Because I have to move all this over because we're going to send our data to the alt mempool here. The alt mempool is going to call the EntryPoint. We need to tell the EntryPoint to then call our account and then have in that same data that we signed, have the minimal account call USDC. So hopefully that makes sense here. So we have the function data for calling the USDC. We also need to get the function data to call the execute. So we're going to actually wrap this up in call data. So we wrapped this up in call data in function data. Now we need to wrap this up in call data as well. So we're going to do bytes memory execute call data. And this is the data that's going to be used in order to tell EntryPoint to call this function, which will call the USDC. Bytes memory execute call data equals abi.encode with selector minimal account minimal account dot execute dot selector comma destination value and function data. So this execute call data is saying, hey, EntryPoint contract, where is it? EntryPoint contract, call our contract, and then our contract, call USDC, right? Minimal account, call this execute function, and then inside this execute function, call USDC. Make sense? Great. We have this execute call data. We now need to use this call data to create our packed operation, right? So this packed user operation, because this is what the alt mempool needs to get. So we're going to have our sender, nuns, blah, 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 all this good stuff here. What's cool is now that we have this send packed user operation, we need to do equals new send packed user operation to actually initialize it. So now that we have this contract, we can just pop this stuff into our send packed user operation. And what are we going to call? Generate signed user operation with the call data and the config. And this is going to return what? It's going to return our packed user operation that is nice and signed. So we're going to have to actually import that as well. So let me copy this. Did we not import that yet? We have not. We can actually just import it from the send packed user operation, which is kind of cool that we can do that like that. But we're going to say packed user operation, packed user op equals send packed user op dot generate signed user operation execute call data comma and our helper config, I believe. What is it? What does this take? It takes the network config. So not the helper config, but we're going to do helper config dot get config. So helper config dot get config. So our helper config is going to give us the network config. We're going to pass that to here, and this needs to be memory like so. So, and this cannot be view because we're calling this, and this could potentially deploy mocks. So, okay, cool. So we have our packed user operation. Finally, it should be signed. It should all be peachy hunky-dory. It should all be good. Now we can finally do our act here, which is going to be where we recover, where we take this, where is it? Packed user operation, where we take this signature and we'll say, hey, let's use this public private key cryptography thing and figure out who actually signed this. We can always derive the public key that signed this. We can't always derive the private key, obviously, because it's the private key, but we need to ask the question, hey, is the person who signed this the right person? So we can go in here and we can do our little ECDSA recover. And we're gonna have to import that as well from our wonderful friends at OpenZeppelin. So a little import ECDSA from at openzeppelin/contracts/utils/cryptography/ECDSA.sol like this. And we can finally, down in the bottom, down in our act here, where is it? Down here. We can finally do ECDSA.recover this. And if we look in this and we look up that function recover, it takes a hash and a signature. So this is going to be the user operation hash, and this is going to be the signature. So if we scroll down, we have this whole packed user operation. We need to convert this into its hash. Don't worry, our friends at the entry point, remember they have this function get user op hash, right? Which calls user op.hash, blah, blah, blah. And this is a little bit cheeky, actually. It's a problem that I ran into for a while when I was first learning this. I was like, hey, is the hash hashing all of this? Because you can't get the signature of the whole hash if you hash the signature first. Like what the heck? What is it actually hashing? And the entry point is kind of tricky. If you scroll up in here, there's like a library that they're using. User operation lib for packed user operation. And if we go to this user operation lib, there's a function in here called hash where they have this, it has this function called hash where it calls encode. And this basically encodes everything except the signature. So there's some stuff going on behind the scenes actually to hash the whole thing a very specific way without using the signature, which is why, again, we always want to make sure we're getting our hashes with the get user operation hash with whatever entry point that we're using, right? So, because the hash isn't, because we could 100% just hash this ourselves, but maybe we do it slightly differently than the way the entry point does it, and we'll lose our minds because we don't hash the right way. So actually, before we do the act, we need to get the hash. So we'll do bytes 32 user operation hash equals entry point. Oh, we need to get the entry point. So we'll do IEntryPoint config dot, or do we have the config? No, we should have gotten the config, but helper config dot get config dot entry point dot get hash, and we'll pass it this packed user op hash here. So we'll get the hash, and now we can finally pass this in to the recover function, although this isn't quite exactly right yet either. We also need to convert this to a .2eth signed message hash. There's a lot of getting the format right in here, so we'll always want to kind of keep that in mind, which means if we're doing that, we got to scroll back to the top. I know a lot of stuff here, and we're going to have to say using message hash utils for bytes 32. If you don't do this, stuff won't work and you'll be sad. So let's get that as well. Import message hash utils from at openzeppelin/contracts/utils/cryptography/message hash utils.sol like this. And then now down here, we convert the user operation hash to the correct format of the hash, and then we can pass the signature. So we'll say user operation hash dot signature that we just created from this function here. Oh my goodness. And this is going to give us an address. So we'll say address actual signer equals this. And we can finally do a little assert equal the actual signer is going to be the owner, right? Because we can only, this should only work if the minimal account owner does the signing. So we'll do minimal account dot owner like this. Woo! I know that was a lot of stuff going on here, but let's run this as a test. Moment of truth here. Oh, and then I did this wrong. Contracts. There we go. So moment of truth here. Oh, IEntryPoint. Oh, we got to import the entry point to, is that in send packed user ops? It sure is. So we can import it from there actually. IEntryPoint. So now we can finally do a little test on this. Scroll back. Oh, just kidding. Not quite yet. I also messed something else up here. Message hash. I should get good at spelling, huh? That's usually my weakness. User operation hash dot signature. Oops, sorry. This is packed user op dot signature. Cool. Now we can finally run this. Let's grab this test here. Clear everything out. Forge test dash dash empty paste dash vvv. Moment of truth. Aha, interesting. We're getting this error. No wallets are available. Now, the reason for this is when you're working with scripting, like we are, right? In our scripts here, we have this send packed user operation and we do this sign here, right? So Foundry is smart enough to know that, okay, if you're doing a script, right? When we do forge script dash dash account or dash dash private key, if we have that, it'll say, okay, that account is quote unquote unlocked. And anytime you do something with a private key in an unlocked account, it'll go through. However, when we're just running forge test, right? Like we're doing right here, we're not passing in an unlocked account. So Foundry gets to this line and goes, nothing's unlocked, even though even in our helper config, we're using the default wallet. Also, we're gonna have to refactor this just a little bit because I messed something in here up. But in any case, so what we actually have to do is we have to be a little bit clever and use a workaround for this specific line here. So we're gonna have to do a little bit of a workaround here for this signing to actually work when we're working on a local chain or when we're working with a test versus when we're actually going to the wild and use this on a test net. And the beauty of this is this actually inspired me to make this issue on the Foundry repo as a new feature. Hey, maybe it would be cool to just automatically use an Anvil default key so that you don't have to kind of do this workaround that we're about to go through right now. And this is the beauty of open source. And maybe by the time you watch this, this will be fixed. Because yeah, as I was recording this, I was like, oh, why do I have to do this workaround? It would be great if Foundry just had this feature. So we made this feature. So any Rust devs watching this who want to take this on, you'll get a big thumbs up from me if you fix this. So, and this also just shows the beauty of open source and how all the tools we're working with here are constantly improving and constantly growing, which is why I have to consistently remake all of these videos. All right, cool. So let's refactor this for working with local tests. Anyways, so we're back here. We're going to need to refactor this and we're going to need to do a little bit of helper config stuff that we've done before. So a lot of the times, instead of doing all this stuff here, we'll make a code constants chunk at the top. I'm not going to do that here, but this would be a little bit better if we made like a code constant and we inherited it and blah, blah. But this is just kind of our fun code base. But if you are here at this point in the course, you already know how to do all that. So we're going to go ahead and skip that for now and we do kind of the hacky way. So in our script here, we're going to say if block.chainID equals 31337. We're actually going to do this a little bit differently. So we're going to take this VAR and S. We're going to do VAR and S like so. We're going to initialize them as blank. And then we're going to say if block.chainID equals 31337, then we're going to do vm.sign and we'll do v, r, s equals vm.sign. And instead of config.account, we're going to do the uint256 Anvil default key like this. And we can grab this by just running Anvil, getting kind of the main key here, killing Anvil, pasting it right here. So this will now be the Anvil default key. So if we're on a local chain, we're just going to use Anvil here. And then we're going to say else. We're going to do all this stuff here. We're going to swap this out with VAR and S like so. So now, since we're using the Anvil default key for our local chain development, we're going to have to go back into our helper config. And actually, we need to refactor this anyways. And we're going to have to go down to the bottom and update this so that instead of working with the Foundry default wallet, we're working with Anvil by default here. So up at the top, we're actually going to comment this out. And now we're going to say address constant Anvil default account equals, and that's actually where we're going to pull Anvil back up and then grab this account here equals this. We're going to grab this Anvil default account and we're going to use the Anvil default account instead of the Foundry default wallet. Now, the other thing that we're going to have to do, because I forgot to do this, is local network config equals this, and then return the local network config. If you didn't do this part, this would just always be true and you would just constantly be deploying mocks. So we don't want to do that. So now we're using the Anvil default account, so that when we use our user operation, we will sign stuff with the Anvil default key, and then all of our tests should work so long as we work with the Anvil default account. That does mean that back in our deploy minimal though, we're going to have to do vm.start broadcast config.account, and then also transfer ownership to config.account, just to make sure that we're going to transfer right away to the correct person here. So now that we've done that little bit of a refactor, let's rerun our test here. What do you know? We do indeed pass. So this means that we've actually successfully written a code base that we will sign our user operation methods correctly. So we've got this kind of huge script in here. Well, it's actually not that huge, which will generate a signed user operation. And it's slightly different for working with local chains, but when we're working with a real testnet, it's going to use this and it'll work perfectly. Trust me, I'm going to do it in a little bit, don't worry. And we're actually correctly signing these user operations. Very nice. So now we want to get to the most important test, and then actually we're going to do one more test as well. Test validation of user ops. So this is where we're going to do what? Well, we're first going to sign our user ops. Then we're going to call validate user ops with our signed user ops. And then 3, we're going to assert the return is correct. All right, so let's do it. And then we're going to actually do one more. So then we're going to do a final function, test entry point can execute commands. And that's going to be our final test here. And the reason, of course, we want to test this is because, once again, who is actually sending these user operations? Well, it's going to be these alt mempool nodes who are going to submit the transaction to the entry point. So we need to make sure that those are working correctly here. So let's do this test validation of user ops here. And luckily, we can actually reuse a lot of the code that we've used up here. And by a lot of the code, I literally mean like all of this. So we can kind of save ourselves some time by copy pasting that user operation hash. Then we're going to get into the actual act here. So we're going to do exactly what we did before, but instead of just testing that we can recover correctly, we're just going to test that validate user op actually returns correctly. So we'll do a little vm.prank, the address of the entry point. I guess we're going to have to do this. I probably should have just initialized this at the beginning, huh? Well, I don't need this address either. Helper config.getConfig.entryPoint. We're going to be the entry point because in our minimal account, right, validate user op can only be called by the entry point here. So we're going to be the entry point. We're going to say uint256 validation data equals. And remember, we are kind of just having some real minimalist validation data, but technically you can add a ton of stuff into your validation data. So we're going to say uint256 validation data equals minimal account dot validate user op. We're going to need to give it the user operation hash. And then we're also going to need to give it this missing account funds. Now, for this, we can kind of just pick some random big number because again, this is just going to be sending the money to the entry point. And for just the validation, it doesn't really matter. For the actual call, it'll matter, but for just validation, we can do whatever. So I'm just going to pick kind of a random number here. We're going to do uint256 missing account funds. We're going to say 1E18. That's probably plenty. That's probably actually way too much, but again, random number. So we're going to get this validation data. Oh, packed user op, excuse me. And now technically we should parse this validation data because our function here is actually pretty simple. It's just kind of returning what? It's returning 0 or 1, right? Or what is this? Yeah, 1 or 0. But technically, this validate user op, if we go to the iaccount.sol, the return validation data is actually like has a ton of data packed into it. So we probably should go ahead and parse the validation data. But since our code base is pretty simple and we just know it's returning a 1 or a 0, we can assume it as such, right? A 1 is going to be failed, a 0 is going to be a success. And we are assuming that this is actually indeed a success. So what is it? 0 is a success. So we're going to say, okay, assert validation data equals 0, or excuse me, assert equals validation data and 0. And now we can test this as well. Test --mt, paste that in, and that passes as well. Okay, awesome. So we've tested we're doing all of our crazy signature stuff correctly. We've tested that our minimal account validation is working correctly. Now let's just finally test what we really care about, which is going to be that the entry point can actually execute commands based off of our kind of crazy nonsense, right? So let's do this last one, and then I'll show you exactly what this looks like end to end on a real actual network. And then once we do all this stuff here, we can move over to ZK Sync and we'll show you how to do this whole process on ZK Sync, which from a DevOps perspective is actually a lot simpler because they have native account abstraction. Very exciting stuff. And the reason I'm so particularly excited about you learning account abstraction is because a lot of people still aren't really using this to its fullest. There is so many cool things people can build with this. So you are unlocking a crazy skill just by learning this. So anyways, let's do test entry point can actually execute these commands here. So let's scroll on up, and you already know we're probably going to want to do all of this stuff again, right? So I'm going to actually, once again, copy paste. We're getting the destination, the value, creating the function data, the execution call data, creating the packed user operation, and then getting the user operation hash. We're getting all that good stuff here. And that's what makes writing this test actually so much easier because we've already done most of it. But what we do need to do is we actually need to fund our account, right? Because we don't have kind of this optional paymaster thing. So when these alt mempool nodes go to submit this transaction, they originally pay for it. And they're going to be like, hey, we need to be reimbursed for this. We're pulling it from you. So you better have the money. So we're going to go ahead and just do a little vm.deal address minimal account like this, and we'll just deal 1E18. I know this is kind of a magic number and not best practice, but you know, you get the picture. Then we'll do a little act here. We'll do a vm.prank. And here's what's cool is we can actually be a random user now. So we're going to prove that a random user, basically any alt mempool node, can submit this to the entry point. And as long as we sign it, you know, we're doing it with our MetaMask, not with Google here. As long as we sign it, anybody can send our transaction, which is kind of wild. So vm.prank, and all they're going to do is on this entry point contract is call this function handle ops. That's it, which we're going to pass our ops, our packed user operations, which is just going to be a single user operation. And then the beneficiary, who is the person to actually get the fees, which we're going to give to random user, right? Because they're the one actually executing this transaction. So we're going to give them the fees for actually doing this. Thank you, random user, for sending our transaction here. So all we have to do is do helper config.getConfig.entryPoint. Yeah, I should have saved this earlier, but you know, IEntryPoint helper config.getConfig.entryPoint dot handle ops. And all we have to do is pass in the array of this packed user ops. So let's actually also do a little packed user operation array memory ops equals new packed user operation array of size 1 here. And then we'll say ops of 0 equals packed user ops like this. So handle user ops will pass in this ops array. We'll give random user. Is it random user? Random user. Oh, I didn't capitalize the U. Okay, well, we'll give random user the fees for this. And then we can just do an assert, finally, packed user operation, packed user, there we go. And then we can do an assert. And we're going to do the exact same assert that we did when just our EOA was the one to call this. So we're going to do this assert right here. because we're doing this mint assert here. So let's scroll on down. We'll do assert, boom, random. Oh, and then we make this payable as well, so it doesn't error on us. User operation hash. Oh, we don't even need the user operation hash because that's inside of our handle user ops. And let's go ahead and let's test this. Forge test dash mt, paste it in dash vvv. Zoom in just a little bit, and it failed. Whoops. So since you're at this point in the course, you now are a little bit better at debugging. You're a little bit better at understanding what's going on. Stuff like this is pretty much going to define your life. Debugging stuff and figuring out where to solve it. So we're going to do a little bit of a debugging exercise. We're going to solve this. We're going to fix this. And then we're going to move forward in life. And this is going to be a great time for you to pause the video and try to see if you can debug this yourself. Of course, if you got the same issue, hopefully you did because you've been following along. Because guess what? This is coding. Coding is a lot of the time it's going to be figuring out why you got certain errors, right? And it's going to be going through all the debugging skills we've been learning, talking to ChatGPT, maybe Googling it, maybe even going on YouTube for the error. So pause the video, go ahead, try to debug this yourself, and we'll come back in a minute. For something like this, ChatGPT will definitely not be very helpful. So let's go ahead and jump into some debugging practice. So Foundry has some really nice tools where we can actually do forge test dash debug, and it'll drop us into kind of this really low level debugger here, where it has all the opcodes and everything that's going on here. So one of the tricks that I like to do is hit Shift G, and this will bring you right to the end of where it actually reverted. And in kind of the bottom here, we can see the line and the code of Solidity where this actually had an issue, right? So we're looking kind of right here. Now what we can do is we can start walking backwards to see, okay, what was the line in this handle ops command that actually failed? Because the output we got from Foundry before wasn't really super helpful. So I'm going to start pressing the K keyword. If you look at the bottom, there's kind of this JK previous next opcode. This is opcode by opcode. We haven't gone over opcodes yet. We go over that in the assembly course. You can go ahead and check that out later if you want. But we'll just go ahead and start hitting J, which will walk us back through kind of the code base. At some points, Foundry will get a little bit confused. It won't exactly be sure what line we're pointing to, but we'll keep going back. And eventually we'll land here. So it's saying try ICountSender.validate user op. And this is the line that is having issues. But we tested validate user op. Validate user op is working great. ICountSender. So this sender should be what? This sender should be the minimal account. Okay, well let's quit this by pressing Q. Let's go back and let's see. Okay, get signed, user operation. Okay, generate user, blah, blah, blah. Let's go see what this is doing. Sender is going to be sender. Okay, who are we assigning to sender? Config.account. Oh, we're setting the wrong account. Now we could 100% confirm this too by actually going to the IEntryPoint.sol, finding this line here, right? And I've kind of already cheated. I've got these added right here and doing a little like console.log, making sure these are the correct senders, the correct addresses, etc. So this would be another way to do this. Of course, you would have to do kind of a clever import. So if you want, you can go ahead and do like a clever import here in your mock entry point here and import console2, print them out, print out those values, etc. So, but in any case, yes, this is wrong. This should be the minimal account. So we're going to need to do a little bit of a refactor here. So call data, config. Yep. Okay. So we're actually going to need to have the address minimal account passed in here as well. And it's this minimal account instead of the config.account that we're going to have to work with. So same thing with the nonce. We're going to have to use minimal account here. And since we're updating this, any place that use this is also going to have to get updated. So this is all going to be fine, but all of our tests are going to be kind of messed up. So in here, we're going to have to do a little comma, address, minimal account. And I'm just going to copy this whole bit right here. So great. That looks good now. We're going to have to do a comma here, address, minimal account. Okay, that looks good now. We're going to comma here. Okay, that looks good now. any place else. I don't know, let's do a little forge build, see if stuff's actually working. It sure is. Okay, and now let's rerun the test and let's see if that actually works now. AA25 invalid account nonce. And if you want to go ahead and debug this one, feel free. Or I can just tell you, but I highly recommend you pause the video and you go ahead and try to figure this out yourself. But basically, our vm.get nonce, this returns essentially the wrong nonce. The entry point also has a get nonce function, but we want to do get nonce -1. Let's run this now for the final time. And we will finally see that everything passes successfully. Fantastic job getting this far. So I know we just went over a lot. So let's do a quick summary on all the amazing things we just learned and the power that you just unlocked for yourself. So we created a minimal account, which takes advantage of Ethereum's account abstraction, or really any EVM compatible chain that supports this. Account abstraction allows us to define anything can validate a transaction, not just a private key. Maybe our friends want to validate it. Maybe our Google session key wants to validate a transaction, whatever you want. All we have to do is code a smart contract that says, here is what can sign my transactions. Once we deploy this, when we actually want to send an account transaction, we first sign the data and we send it to a group of alt mempool nodes. These nodes are going to be the ones to combine everything into a single user operation. They're going to combine everything into a user operation and call the handle ops function on an IEntryPoint contract. This contract will then do a lot of validation. And if it looks good, it will call your account and your account will call the dApp it's working with, etc. This is really fantastic because you can sign and send transactions where you don't pay any gas. If you have set up a paymaster where somebody else is going to pay for the gas, you can code any type of validation into your account. You can say my Google session keys is going to be the one to sign my transactions. My friends are going to be the ones to sign transactions. I'm going to add a spending limit. I'm going to give my children an allowance on their account abstraction transaction. I'm going to give them a wallet that they can use for now, but I'm going to put parental controls on it where I have to approve all their transactions. You can code literally any rules that you want into your account. We built a minimal account that uses this account abstraction. The main function that we needed to get correctly was validate user operation. Instead of sending a regular transaction object to the blockchain, those alt mempool nodes will send a user operation to the entryPoint.sol contract, which will call your contract and call the custom logic that you built for your validate user operation. If the transaction is valid and the signatures associated with the transaction are valid, it will then execute the transaction and do whatever you want here. We did some very basic signature validation, and we even wrote a quite badass script to generate signed user operation data, generate unsigned user operation data, and then actually send the handle ops transaction directly to the blockchain. So at this point, you've learned what I want you to learn for Ethereum account abstraction. This is a great time, if you like, to go ahead, take a break, go to the gym, get some ice cream, get some coffee, whatever you want to do. But we're not done with account abstraction. We have understood this wonderful process on Ethereum. However, as we've kind of seen, it's quite convoluted. So we are now going to learn account abstraction on ZK Sync, which has this built in. The only difference is you need to send a type 113 transaction, and that's it. Because they have what's called a combined mempool. They have the alt mempool and the normal mempool are both just the mempool, which is really cool. So game plan moving forward, we've done this. We're just going to deploy a user op onto Arbitrum, and then we're going to do the whole thing again for ZK Sync. Like I've been saying, now's a great time to take a break, go to the gym, get some ice cream, get some coffee, and we'll see you soon. But let's do it. So before we actually go to ZK Sync, let's go ahead. Let's actually send this. Let's actually run this for Arbitrum. And if you go on the GitHub repo associated with this course, you can go ahead and actually see kind of the make commands that we're going to run. I'm just going to go ahead and do it right here because it's not super important that you actually run the scripts, but it is cool just to see kind of it all happen. For us to deploy our code base, we're going to do a little forge script script/deploy minimal.s.sol --rpc URL. We're going to be using an Arbitrum RPC URL. I've already sourced my .env and I already have this in here. Like I said, I'm just kind of quickly speeding you through this just so that you would see what this would look like. We're going to do --account is going to be my small money, aka my burner account. This is a burner account that I deploy stuff with. Since Arbitrum is a real mainnet, there will be real funds here. So you always want to use a burner account to deploy stuff just in case you mess something up. So we're going to use a burner account or my small monies account. And then we're going to do --broadcast --verify like this. And after this has been deployed, and I've actually already sent it just a tiny little bit of ETH as well. After this has been deployed, we can kind of scroll down in here. We can see this is the minimal account that I deployed. I added some NatSpec and stuff. It's a little bit different than exactly what we coded together here, but here is the code base. And now what we're going to finally do is we're going to send that user operation. And actually we do need to update our script. We actually do need to update this script because I forgot to add the run stuff in here. So let's add the run stuff in here real quick. So we're going to say helper config equals new helper config address. This is where I probably would want to do like helper config.getconfig.ustc, but I'm actually just going to grab the Arbitrum mainnet endpoint, Arbitrum mainnet USDC address. So we grab this, we go to Arbitrum scan, paste this in, boom, native USDC token deployed by Circle to Arbitrum. Okay, cool. So that's going to be our destination. uint256 value is going to be 0 here. Let's do bytes memory function data equals, let's just call the approve keyword. So we'll do abi.encode with selector. We'll say IERC20. Let's import this from @openzeppelin/contracts/token/IERC20/IERC20.sol like here. .approve.selector, and we'll approve, and I'm going to pick myself. This is just another one of my wallets that we're going to go ahead and approve here. And then we'll choose an amount. We'll do 1 E18. Yes, this isn't the best code because I'm just kind of showing it for this video. If you want to go check out the nicer code, be sure to check out the GitHub repo. Then we're going to do the bytes memory execute call data equals abi.encode with selector. This is nearly exactly as what we did in the tests. Minimal account.execute.selector dest value function data like this. We need to import minimal account from src/Ethereum/minimal account.sol like this. Then we're going to say packed user operation memory user op equals underscore get, not equals generate signed user operation. We're going to have the execute call data. What else? We're going to need the config. So helper config.getConfig like this. And then the address of our minimal account, which I'm just going to kind of hard code for now. Boom. Execute call data like that. Then we're going to say packed user operation array memory ops equals new packed user operation array 1, exactly like what we did in the tests. Ops of 0 equals user op. And then finally, vm.start broadcast IEntryPoint. Do we have this in here? Yep, we should do IEntryPoint of helper conf.getconfig.entryPoint.broadcast. .handle ops, and this can be anybody that we want. I'm just going to do config.account here. Config.getConfig. So I'm going to go ahead and kind of speed through this actual deployment process here. What I'm going to need to do in here is I'm going to need to go ahead and add Arbitrum an Arbitrum config. Once I add an Arbitrum config, I'm going to need to make sure all my wallets and stuff are set up correctly. I'm going to kind of speed through doing that, do that behind the scenes. So, all right, let's go ahead. And then of course this needs to be payable. And then a little VM.stop broadcast as well. Okay, so let's go ahead. Let's run this as well. So what we're going to do, forge script send packed user op.s.sol --rpc URL Arbitrum RPC URL -- account is going to be small money -- broadcast -vvv. Now I've actually already run these commands and I've already deployed this minimal account much earlier, and I don't feel like spending more actual gas. One of the things that's kind of rough about testing account abstraction is there's not really a testnet way to test these. So I had to ship it onto a real mainnet, which is why I did an Arbitrum here. So, but like I said, I did this a while ago, and here's the output. So this code base is working wonderfully, and now you know how to do this. We can see we have an internal transaction in here. So we have an internal transaction in here where, if we look at kind of the logs in here, we can see we called handle ops, we had an ops.sender, we had the call data in here, we had everything we talked about, and we had a beneficiary. And what this ended up doing was, we go to the logs here, we scroll down in the logs here, the USDC token gave approval, gave this much approval to this address, and we have successfully made an account abstraction user operation call. Let's go! So you could 100% take your newfound power here and go build some amazingly cool things for the Ethereum ecosystem, where there's a lot of smart contracts, where there's a lot of layer 2s that don't have account abstraction built in natively, and you'll have to do kind of all this funky programming. Or you can follow along with me and we can learn how to do this on ZK Sync. So if you didn't take that break, be sure to take that break, go to the gym, get ice cream, get coffee, get whatever, and then come back, because we're going to do this all over again, but on ZK Sync with native account abstraction. So take a break and I'll see you soon. All right, so let's start jumping into working with ZK Sync for account abstraction. Now, like we were saying, ZK Sync has what's called native account abstraction, where we don't have to do this weird middle step of sending to this alt mempool. We just send to the normal ZK Sync mempool. There's also no EntryPoint.sol. Everything just goes directly to your contract, right? So we get the much simpler setup that kind of looks like this, where you send your transaction to the mempool and you don't even have to spend gas. This is why when we actually did send that transaction, deploy that smart contract in Remix with ZK Sync, we actually had transaction type 113. We were actually just signing a transaction. We didn't actually spend any gas ourselves. We sent this data to a ZK Sync era node, and it deployed our contract and then actually did end up charging us afterwards to spend gas because somebody needs to spend gas. But this is why we hit sign instead of send transaction. So we signed all of this data, which they then sent, and since ZK Sync has native account abstraction built in, it was able to automatically charge our wallet. And all this happens kind of auto-magically. And don't worry, this is my testnet account. I'm not this rich. Now, to get working with account abstraction on ZK Sync, we're going to install this package called Foundry Era Contracts. This is a mirror of a lot of the system contracts in the ZK Sync system. We're going to learn about this thing called system contracts that ZK Sync has, which enables a lot of these really cool automagic things happening in the background. For the duration of this curriculum, anytime you see like era contracts or Matter Labs era contracts, we're going to work with this Cyphren Foundry era contracts instead. I've made a lot of tweaks to the code base so that's easier to work with and easier to use. So this is what we're going to be working with. At some point, I'll put like a little disclaimer at the top here that says, hey, instead of this, now go use, whatever the ZK Sync team comes up with. But for now, this is what we're going to be working with. So I want you to go ahead to get started, and we're going to go ahead and we're going to go and install this. And let's close all these up. Let's pull up our terminal, do forge, install, paste it in. And for this video, we're going to use 0.0.3. So we're going to say at 0.0.3 -- node -commit, of course. All right, great. Now that we have this installed, we can actually open up our command palette and look for IEntryPoint.sol, but instead of in the account abstraction folder, we're going to look for it in the Foundry era contracts folder. So if you can't find it like that, you can just open up your lib, Foundry era contracts, SRC, system contracts, contracts interface, IAccount.sol. And I would like you to also open up this default account.sol, which at the moment is completely commented out. Although depending on when you watch this, it might not be commented out. So the reason I'm showing you these is because something really interesting that zk-sync does. On Ethereum, there are two kinds of wallets. You have kind of your classic traditional externally owned accounts. This is going to be your MetaMask, this is going to be your Rabby, etc. And then you have your smart contract wallets. These are going to be your multi-sigs, your account abstraction accounts, which we just created. And these are basically the two different kinds of wallets. Now, this causes a lot of issues though. Whenever you're coding transactions, sometimes you have to know if it's a smart contract wallet or not. Some people have code where they say, hey, you know what? Dealing with smart contract wallets is too complicated. And some of them will even have checks saying, if you're a smart contract wallet, deny the transaction, revert the transaction. And there's a lot of reasons for this, but it definitely makes dealing with wallets, dealing with addresses really difficult. So what zk-sync did was it said, okay, you know what? All EOAs are smart contract wallets. So externally owned accounts and smart contract wallets are basically exactly the same, and we are going to treat them as such. And this default account contract, which again, I've got everything commented out. You can uncomment it to kind of see what this looks like. Every single account, every single smart contract account is set up as a default account. So if we go to our MetaMask here and we take our wallet address and we go to the zk-sync era Sepolia Explorer or Mainnet Explorer, doesn't really matter. We paste that in here. It doesn't look like it's a contract, right? It looks like it's a normal wallet address. There's no contract tab here. Patrick, what are you talking about? Well, the zk-sync Explorer is smart enough to know, okay, the code for this is a default account. So we're going to show it as if it's not a smart contract wallet. So we're going to show it as if it's a normal externally owned account and not a smart contract wallet. However, they are all smart contract wallets, which I actually think is really cool because in this sense, you know that every single address you interact with is going to be a contract and is going to have code. And to me, that actually makes stuff a lot easier. Now, every single wallet, including your EOAs, follows this interface here, which I think is really cool. They have a validate transaction, execute transaction from outside, pay for transaction, and prepare for paymaster. And this looks really similar to what we saw on Ethereum for our Ethereum account abstraction. But again, because zk-sync has account abstraction built in, every single wallet has this account abstraction type functions that we can interact with. And this is one of the things that makes zk-sync so powerful is that it has this account abstraction built directly into the chain. Because of this, it makes doing all this setup much easier, right? We don't have to deploy that entry point contract. We don't have to send our user operations to an alternative mempool, and it cuts out the middleman here. So every single account, every single address will have these functions to some extent, okay? So knowing this, we can now take this knowledge and actually apply it to what we're gonna do here. So we're gonna create I've already created the zk-sync folder. We're gonna create a new file called zk-minimal account.sol, and we're gonna get cracking. And this is gonna be our minimal zk-sync account abstraction account. So we know we need this I account thing, right? We know this is the most important interface. We need our contract to have these functions in order for us to use this account abstraction thing. So let's go ahead, let's import this and start from there. So I'm gonna do import I account lib/foundry era contracts /src /system contracts /interfaces /I account.sol. And do a little toggle word wrap here. So cool. And now we're going to do contract zk minimal account is I account like this. Oh, and then of course, let's do, wow, pragma. Can't believe I forgot that at the beginning. MIT 0.8.24. Boom. Okay. Now it's saying, hey, it should be marked as abstract. Let's just grab these functions in here. Boom. We're going to copy paste them in here. We're gonna get rid of these comments here, but you should add comments. Going to add these little semicolon bits here, or these little curly brackets. And one of the things we're going to need is this transaction, call data transaction. We go back into the I account. It's pulling from this memory transaction helper.sol. So let's actually import that as well. So we're going to do import transaction from, and I'll explain what that means in a minute, lib foundry era contracts /src /system contracts /contracts /libraries /memory transaction helper.sol. So now we have this transaction thing. We have these functions. Let's keep going. So probably the first thing that we're going to need to do here is understand, okay, what are these functions? Like, what are they actually doing? And we can probably tell based off of their names, but let's get a better understanding by going through the interface itself. So the first one is going to be validate transaction. And if we go to the minimal account.sol, this is going to be analogous. This is going to be very similar to validate user op. So in Ethereum, they're called user operations, but since account abstraction is built directly into ZK Sync, ZK Sync just says validate the transaction, because it doesn't care if you send an account abstraction transaction or a regular transaction. It considers all of them transactions. So this validate transaction is going to be the ZK Sync equivalent of this validate user operation. On Ethereum, they're user operations. On ZK Sync, they are just transactions. And what's kind of cool here is there's this transaction struct, transaction call data transaction. I know it's a little bit confusing here. And we're actually going to change these to memory though. Memory to make our coding a little bit easier, because we don't really want to have to do a lot of like memory to call data conversions here. But ZK Sync has this transaction object, and I have created this memory transaction helper.sol that you guys can check out. The reason I created this was to, again, make a lot of the development here a little bit easier. Some of the conversions between call data and memory kind of break a lot of things. So I just said, screw it for this tutorial. We're just going to work with memory. We're not going to deal with any of that conversion stuff and make your lives miserable. But in this memory transaction helper, there's this struct transaction. So this is the structure used to represent a transaction in ZK Sync. And what's cool here, let me zoom out just a little bit. I know it's this kind of massive struct, but what's cool here is every single transaction, anytime you send a transaction on ZK Sync, it's this struct that's used to represent it. And so if we kind of go through this, we see transaction type. So Kira went through this a little bit on the different transaction types, type 1, type 2, type 3, and the account transaction types of 113, aka OX71. We have a classic from, a classic to, a gas limit, more gas stuff, more gas stuff, more gas stuff. A paymaster. Now this is going to be the exact same as a paymaster in the Ethereum world. They're built natively into ZK Sync. You have a nonce, you have value. There are some reserved keywords for maybe in the future. Yeah, for this in the future, we might want to add some new fields to the struct. So just some reserved stuff. Obviously the data, signatures, and then this factory depths, which we will get to in a little bit. These are actually really important. Paymaster input, and then reserved dynamic. Again, this is just kind of like a reserved extra space in the struct here. Every single transaction can be fit into this struct here, essentially. So when we in ZK Sync send an account abstraction transaction, all it's going to do is say, okay, transaction type is going to be 113. From is going to be, our ZK minimal account. 2 is going to be blah, 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 etc. We could also send kind of a normal transaction type 2, and the account could be from whomever, right? So anytime we send a transaction in ZK Sync, it can be every single transaction is at some point put into a struct transaction, into this struct here. So when we do validate transaction, we send a transaction hash, a suggested signed hash, and then the actual transaction itself. And when we call validate transaction, one of the parameters is going to be the transaction struct, which we will populate, of course. Now, what are these two? The transaction hash and the suggested sign hash. Well, let's go back to our I account here. So the suggested sign hash is going to be the hash of the transaction. So the TX hash is the hash of the transaction to be used in the Explorer. And the suggested signed hash is going to be the hash of the transaction is signed by the EOAs. We are going to ignore these right now. We're not going to use them. This is something that something called the bootloader is going to work with, which again, we'll talk about in a little bit. But for now, we're going to pretend these don't exist, and we're only going to focus on this transaction. Now, what this returns is going to be the magic value that should equal the signature of this function if the user agrees to proceed with the transaction. So it's a bytes for magic, but you can kind of think of this as, again, like a true false. Because here, if we want to have this return true, all we would do is say like return IAccount dot validate transaction selector. Boom. If we want this to return what essentially is true, this is all we would return. And just like in minimal account, how this returned this validation data, which has like a 0 and a 1 and some other stuff, this is kind of the equivalent of that, where you just return the function selector, and that's the equivalent of saying the transaction is valid. So we're going to delete that for now, though, because we're going to actually learn how to validate this pretty soon. So we're going to validate the transaction. We're only going to focus on this transaction thing. We're going to ignore these for now because we have to learn something in a little bit to understand these. Next, we have execute transaction. What do you think this one can do? Well, let's go back to the minimal account. In our minimal account, we had this execute function, and we put this modifier on it, require from entry point or owner, or either the owner of this contract could call this execute or the entry point, which was that account abstraction contract. This execute transaction is the exact same. If we want to directly call this function with an owner without going through the account abstraction proxy that is zk-sync, we would just directly call this execute transaction function. And again, this takes a transaction hash and a suggested signed hash, which again, we're going to ignore for now, but it's given this transaction object. So we're going to keep ignoring these for now. Transaction memory transaction, boom. This is to execute any transaction. Next, we have execute transaction from outside. Let's go into IAccount, take a look at this one. So this one doesn't have any comments here. However, what this one is this is going to be the function that gets called for somebody else to execute a transaction. So this is basically where if you sign a TX, send the signed TX to your friend, they can send it by calling this function. So basically you create a transaction, you sign a transaction, you send it to your friend, and then they call it with this function. So execute transaction and execute transaction from outside essentially do the same thing. It's basically just gonna be a higher admin calling this versus execute transaction from outside is going to be basically anyone being able to call this. You can kind of think of this as the function that the IEntryPoint contract would have called in the Ethereum world. And when we create this function, we're going to have to validate the transaction and then execute it. Pay for transaction. This is similar in our minimal account to pay prefund, which was an internal function here. In order to do account abstraction, somebody needs to pay for the transaction. So this is where you encode who is going to be paying for the transactions. It could be your account, it could be somebody else, and then pay for paymaster. This is the function that gets called before you actually pay the paymaster if you have a paymaster. And again, a paymaster is somebody who is going to be paying for the transaction. So this is essentially what we want to do. So anytime somebody sends an account abstraction transaction, here's basically going to be the process. There's essentially two phases. There's the validation phase, and then there's the execution phase. So the first thing that happens is the user is going to send their transaction to the zk-sync API client. I have here sort of a light node, but you can basically just think of this as sending it to Ethereum, right? So you send to the zk-sync node. Then the zk-sync node checks to see if the nonce is unique by querying the nonce holder system contract. Wait, what? By querying the nonce holder system contract. What is that? And this is one of the biggest differences between Ethereum and zk-sync. zk-sync has a large collection of these things called system contracts. They're smart contracts deployed on zk-sync by default that do a whole bunch of very interesting things. Let me show you a very specific example. This is address 006. So it's all zeros and then 806. And this is what's known as the contract deployer system contract on zk-sync. If you scroll down, you look at the contract tab, you'll see a whole bunch of constants, and you'll see this contract deployer.sol. This is a contract that zk-sync has on it by default. So just by running a zk-sync node, you automatically get this contract deployer smart contract. And this contract governs actually deploying smart contracts. Yes, I know, crazy. So on Ethereum, to deploy a smart contract, all you have to do is send an Ethereum transaction containing the compiled code of the smart contract without specifying any recipient. Doing that, the Ethereum nodes go, there's no to here. They're probably trying to create a smart contract. I'm going to take their code and deliver it as such. On zk-sync, that's not how you do it. You actually call a function on here, create to account, create account. You call one of these functions, and it's these functions that will actually create a smart contract. So zk-sync has a lot of these system contracts at very specific addresses that govern a lot of the functionality that goes on in zk-sync. The contract deployer being one of the most important ones. This is also why when trying to deploy a smart contract to zk-sync, we can have a hard time. So Forge Create with Foundry does this Ethereum edition, right? It sends an Ethereum transaction containing compiled code of smart contract without specifying a recipient. This is why we have to do Forge Create -zk-sync -legacy, because Foundry zk-sync sees this, sees this and goes, okay, they're probably meaning to call this create function on the contract deployer system contract. So this is why actually a lot of these different commands don't quite work for zk-sync as of today with Foundry because of these system contracts. Now, these system contracts actually make it a lot easier to interact with zk-sync, because if you want to just do anything, you just send a transaction and you say, hey, I want to create an account, and you call the create function. And arguably that's actually much simpler, but it's one of the biggest differences between zk-sync and Ethereum is going to be these system contracts. In the zk-sync documentation, there's a ton of information on the different types of system contracts, what they do, and then how to interact with them as well. So in any case, put this a little bit earlier. So this is going to be the life cycle of a type 113, aka a 0x71 transaction. So this is the life cycle exclusively for an account abstraction transaction. Okay. So phase one in the validation, the zk-sync API checks to see the nonce is unique by querying the nonce holder system contract. So another one of these system contracts is this thing called the nonce holder. What this contract has is it has a ton of mappings where it has the nonce of every single smart contract on zk-sync. Yes, so you can look up the nonce of every single smart contract on zk-sync by querying this nonce holder contract. So this nonce holder smart contract has a mapping of every single account address, and the nonce that they currently are working with. The second step in a zk-sync account abstraction transaction is going to be checking the nonce holder system contract, making sure that it's good. Then the zk-sync node is going to call validate transaction, which must update the nonce. So in our zk minimal transaction, whenever we send an account abstraction transaction, this validate transaction function is going to be called. And if this bytes magic returns a valid magic value, then these zk-sync nodes will go, cool, this transaction looks good. But if not, it will say, no good here. So then a question should probably come up. Okay, so we're calling this validate transaction thing, but it must update the nonce. So then this is actually not going to be a view function. This is going to be like a legit transaction. So the question is, so who is the message.sender when this is called? So are you telling me, Patrick, that anyone can call validate transaction and then just update the nonce? That sounds insane. Well, that would be insane, which is why we don't want to allow that. So Patrick, you're saying we must update the nonce. So who's the message.sender when this is called? Well, whenever you send a type 113 transaction, the message.sender is always going to be this thing called the bootloader system contract. Now, the bootloader system contract, you can kind of think as like the super admin system contract of all these system contracts. So whenever you send this type 113 transaction, it will be rerouted to this bootloader system contract. This is how zk-sync has account abstraction built in. It has this bootloader system contract. You can kind of think of this as the IEntryPoint smart contract on Ethereum mainnet. So for everything that happens in here, the message.sender is always going to be the bootloader system contract. Make sense? Okay, cool. So Sync API client, aka the zkSync node, will call this validate transaction, which is going to update the nonce. And we're cool with that because it's going to be the bootloader system contract that actually is doing that call. So we're probably going to want to restrict the functionality of validate transaction here so that only the bootloader contract can call this once, because we don't want anyone updating our nonce willy-nilly. Next, the zkSync API client, aka the zkSync node, will check that the nonce is actually updated. So if this doesn't update the nonce, whole transaction will revert. Then it will call pay for transaction, prepare for paymaster, and validate and pay for paymaster transaction. So basically, it will call and do all the functionality for paying for this transaction before actually sending the transaction to see if there's enough money to pay for it. And once this is called, it will verify that the bootloader gets paid. So there needs to be a balance inside of the bootloader, kind of similar to what we did with minimal account, how we sent we have message.sender here, but this is the entry point, how we sent the entry point funds. Kind of same thing with zkSync. We just have to send the bootloader funds. And then if it passes all of this, the validation phase is done. And then we move on to the actual execution phase of the transaction. So in the actual execution phase, this zkSync API client will pass the validate transaction to the main node / sequencer. So everything in validation kind of happens in this, like we said, this light node. So you can kind of think of the zkSync system as having a whole bunch of light nodes or API client nodes, and then the main node, the main sequencer node. So the main node and sequencer, as of today, are both the same, but maybe in the future they get split up. Kira does a great job talking about why centralized sequencers are bad. And as of today, zkSync is working on decentralizing the sequencer so that there's not just one. But as of today, there's just one. The reason that they kind of have this split up into two is it would be very bad if the main node was stuck validating transactions all day. So they have this kind of client API, this light zkSync node do all the validation. Once the zkSync light nodes validate that the transactions are good, only then do they pass it over to this main node so we don't get a denial of service attack. If you're unfamiliar with that, don't worry about it. Then the main node will finally call this execute transaction function. So very similar to how the minimal account, we have execute, where we have require from entry point or owner. We're going to do the exact same thing in here. This execute transaction, we're going to say require from bootloader. And then finally, if a paymaster was used, the post transaction is called. So if there's any type of post transaction, we're not going to be worrying about that, but that would then be called. So that is the whole process of running a type 113 account abstraction transaction on zkSync. This is going to be the whole process, and we're going to see that flow go through here. Now you might be asking, hey Patrick, what about execute transaction from outside? Well, we're going to set this up so that anybody can actually call this, and they just still have to run through the same transaction validation as everybody else does. So this is where the bootloader calls it. This is where anybody can call it. You'll see what I mean when we build it out. But this is the flow that we're looking to do. We're going to work with these system contracts. We're going to do a lot. All right. So even though we've barely even coded anything, we've really just kind of been talking. We've already gone through a lot. So I want to take a quick breather, a quick refresher on kind of all the things we just learned, because I just threw a lot at you, and it's okay if it doesn't quite make sense the first time here, right? So follow along with me, code along with me here, and I promise you it'll make sense. Be sure to use the GitHub discussions. Be sure to ask questions in the community, because this is a crazy unlock. This is a crazy power up that not a lot of people are taking advantage of. So let's do a quick recap of all the things we're doing here. So an account abstraction transaction is called a type 113 transaction. And unlike Ethereum, where you actually have to send your transaction to an alt group of nodes, which will then send it to an Ethereum node, on zkSync, all you have to do is say, hey, this is an account abstraction transaction, and you can send it directly to the normal zkSync nodes. When you do that, a zkSync system contract called the bootloader is going to take ownership of that transaction. In zkSync has a group of what's called systems contracts. These are special contracts in the zkSync ecosystem with very unique privileges, locations, and update mechanisms. One of the simplest ones is going to be the nonce holder smart contract, which is literally a smart contract that has a mapping of all the nonces of every single account, every single address in the blockchain. When we send an account transaction, a whole bunch of validation happens where the zk-sync node will call validate transaction to increment the nonce. If the transaction is valid, it will then pass it to the zk-sync sequencer to finish executing the transaction. We can additionally sign a transaction and let people call execute transaction from outside, where the bootloader isn't the message.sender, where whoever sends the transaction is message.sender, but we want to make sure they run through the same validation as the bootloader would run through. And of course, if we call execute transaction from outside, whoever is calling this is going to have to pay for the gas, whereas when we do the execute transaction and validate transaction, the paymaster will pay for the gas. So cool. So I know that's a lot, but stick with me. We're going to build this. It's going to be quite cool. And I am going to challenge you after this to build your own codified rules for account transactions. Some really easy ones could be like a spending threshold, and some more difficult and more interesting ones could be like, all right, you're going to sign a transaction with your GitHub keys, with your GitHub session keys. If you do that, that would be very cool. All right, well, let's get cracking building our code base here. And I want to just already clean this up with some headers, external functions, grab that, paste it here, external, and then we'll also do internal functions like this. Boom, because we're going to have some internal functions because we're going to reuse some code across some of these. So the first one that we're going to have to work with, and probably the most important one, it's going to be this validate transaction, right? So we must increase the nonce for this at notice, and we must validate the transaction. Oh, and actually, before we keep going, we should do a foundry up zk-sync. Make sure we're working on zk-sync here. Do a forge build --zk-sync, and we might have to wait a little bit for this. And great, after a little bit of waiting, we actually get an output here. Now there's going to be a lot of warnings in here because a lot of the cheat codes we use in Foundry give basically warnings for zk-sync because again, zk-sync and Ethereum are slightly different. They don't use the same EVM. They don't use the same opcodes. So we're going to get all these warnings, but as long as none of these are warnings with our actual code base that we're going to deploy, these are pretty safe to ignore. And it looks like that is the case. So cool. And we'll periodically be compiling as normal just to make sure stuff works. So we're going to do this validate transaction, and this must increase the nonce. It must validate the transaction. We're once again going to do check the owner signed the transaction, and we'll go into this transaction object again. So we're going to have this be real similar to what we did with the Ethereum minimal account, where it's just the owner. There's a single owner. There's no cool rules here. If you want to go do cool rules later on, you absolutely can. We should also, it doesn't say that we have to do this, but since we're not going to be adding a paymaster, right? We're not going to be doing kind of any of these clever, cool payment stuff. We will also check. We'll also check to see if we have enough money in this wallet to pay for the transaction. And that's pretty much it. So let's go ahead and jump into here. So the first thing we're going to want to do is we're going to want to increment the nonce. So every single one of these wallets, every single one of these accounts comes with a nonce. And it's this nonce holder system contract that keeps track of the nonces. And it's also what we'll have to use to increase the nonce. So you can see there's increase min nonce in here, set value under nonce. There are all of these different methods in here to actually increase the nonce and work with nonces. For us to actually increase the nonce, we have to do what's called a systems contracts call. So calling these systems contracts isn't quite as straightforward as just, okay, drop in the address and call it. Now, making sure we call a system contract actually requires a couple of special things we need to do. On the nonce holder, we're going to need to call this function here. Increment min nonce if equals. So basically, we're going to pass it the expected nonce of our account, which will start off as 0. And if it is 0, it'll go ahead and just add 1, right? So we have this raw nonces address as key, old raw nonce plus 1. So we're just going to increment the nonce by 1 here. So we need to call nonce holder and then increment the nonce of our ZK minimal account. To do this, we actually have to, in our foundry.toml, we have to add a flag underneath remappings. We have to add this is system equals true. So, and this is going to be a little bit confusing. And if it doesn't make sense the first or second time, this is going to be one of those times where I just say, hey, don't worry too much about it. So I asked this question on Stack Exchange Ethereum, and luckily the zkSync team actually responded, and I asked for some clarifications. But essentially, what happens whenever you pass the isSystem flag to the contract, it will inline replace all simulations with their isSystem call counterpart. So calling system contracts in zkSync is actually very difficult. So what the compiler will do, what the zkSync compiler will do, is if you have this isSystem equals true, it'll say, okay, well, anytime I see a very specific call where the data is X, Y, and Z, I'm going to convert that into a system contract call. These are called zkSync simulations. So if isSystem is true, very specific calls are going to turn into a system contract call once it's compiled, right? So if we look in the zkout from our little compilation here, we can even go into, where is it? zkminimal, all the way at the bottom, zkminimal count.json. This bytecode here, this, if you're familiar with EVM bytecode, is not Ethereum bytecode at all. This is zkSync bytecode, which is completely different than Ethereum bytecode. But making a system contract call can be quite complicated. So basically, system is true. It says anytime you see this specific data inside of a call, turn into a system contract call. So, and here's a good example. For example, if there's a simulation like so, call address 25 with data 7 string hello secret thing. If this is a simulation, or basically a key phrase or a keyword or a key call that's equal to the system contract.update nonce holder 1, if isSystem is false is passed to the compiler, the codebase will just stay as this, right? It'll do this weird call to random nowhereville. But if isSystem is true, it'll automatically transform this into system contract.update nonce holder. So whenever we compile a smart contract like this, we need to have isSystem be true or false. And if it's true, anytime it sees one of these very specific calls, it'll transform it into a system contract call. You can almost think of these as like kind of very specific keywords, very specific variables that zkSync searches for whenever it compiles to swap out for a system contract call. So we want to do this system contract call. So we're going to use some tooling to do this system contract call and make it very obvious to us that it's a system contract call, and very obvious to the compiler that it's a system contract call. So we're going to use this library called the system contracts caller to do this. So I'm going to go ahead and import this system contracts caller from lib/foundry era contracts/src/system contracts/contracts. I probably should have put a remapping in for this, huh? /libraries/system contracts caller.sol, like this. Now, this library has a lot of stuff in it. It's got a lot of different addresses, but the main thing that we're going to be using it for is the system call with propagated revert. And it's this function that's going to help us make these system calls, make these simulations without us having to really kind of know exactly what's going on here. So we want to call the system contract. All of this is, if this systems contract stuff like doesn't really make too much sense to you for now, like I said, don't worry too much about it. Just kind of blindly follow along and just know that this is what we have to do to update the nonce. And there's going to be a couple of times when we call one of these systems contracts, and just in order to call the systems contracts, you need to set this isSystem to true. Just know this is how we call these system contracts. We need to update the nonce. So we need to use this system contracts caller dot system call with propagated revert. This is going to help us do that system call. And in here, we need to pass a gas limit to value and data. So gas limit for here, we're just going to do a uint32. Whatever gas is left, we're just going to pass all the gas that is associated with the transaction. 2 is going to be the nonce holder system contract. So we're going to need to get that nonce holder system contract. We can get this from a constants.sol file in the Foundry era contracts. So all of the constants are in here. This is set up for Ethereum. This is set up for zkSync mainnet. Technically, if you look in the true zkSync codebase, these system contracts addresses can actually change, but we've hard coded it for now. If in the future these addresses change, I'll go ahead, I'll update the addresses, I'll update the dependencies. Just go ahead and check the minimal account abstractions. Just go into this makefile and just use the same versions that I'm using in here so that you always know you're using the correct versions. But in here, there's a nonce holder system contract with an address over here. It's based off of an offset. So we're just going to use the address of this nonce holder system contract. So we're going to need to import that as well. Import the nonce holder system contract from lib/foundry era contracts /src/system contracts /contracts/libraries /constants.sol, like this. And so we're going to call the address of this nonce holder system contract. And what's kind of cool is if you're in this constants.sol, you can see the nonce holder is at the system contracts offset plus 0x3. So we can look at the systems contract offset is this. If we take this address and we go to zkSync era explorer, it's basically saying, okay, at 0x8003, this should be the nonce holder. So hold on, let's just do a little pop-up open chisel. We'll do address my addy equals this, or address like this. We look up my addy, boom. It's the address we get. Pop this into the explorer. We can go and see that this is indeed the nonce holder system contract. So that's actually pretty cool. And yep, same thing. It has all the same functions, both the same read and write functions for working with nonces, which is very cool. So we're going to send the gas, the nonce holder system contract. It's going to be the 2. We're not going to send any value. And then we're going to do abi.encode call. So encode call is kind of a nice newer way to do encoding. It's kind of similar to encode with signature, but we're going to call that increment min nonce if equals. So I'm actually going to actually work with that, I'm going to import I nonce holder from lib/foundry era contracts /src/ system contracts /contracts /interfaces /I nonce holder.sol, like this. We're going to say abi.encode call I nonce holder dot increment min nonce if equals comma transaction dot nonce, or excuse me, underscore transaction dot nonce. So this transaction object, as we've seen, it has a nonce value that needs to be sent. So we're going to say increment the nonce, whatever nonce that was given to us, we're going to take that nonce and add 1. And this is all we need to do. I know it sounds like there was a ton we needed to do, but this is really all we need to do to increment the nonce. It's just this one systems contracts call to increment the nonce, and then we're good to go. This also has some return data. We're going to ignore the return data though. Now I know there was a lot here, so I'll do a quick recap again, because this is pretty complicated stuff. So this is what's known as a system call simulation. zkSync sees this and it goes, oh, okay, that's kind of a weird call. I'm not going to let you call the systems contract unless you have isSystem is true in here. Then I'm going to transform this into a systems contracts call. The nonce holder system contract controls all the nonces. It has a function called increment min nonce if equals, and that's how we can increment the nonce of our zk minimal account. So we've incremented the nonce. Next, what do we need to do? Okay, we're going to need to check for fee to pay. We're going to need to check the signature, of course, which we're signature wizards at this point, and then return the magic number. So each transaction is going to require a certain amount to be paid, right? Same as Ethereum. So we have to calculate how much this transaction is actually going to cost. We don't have to do the math for that. There's actually a tool that zkSync has built that will allow us to get that ourselves. So it's called the transaction helper, but we're going to use this thing called the memory transaction helper that I made to make it easier to do pretty much everything that we're going to be doing. So we're going to import this, and actually it's in the same place that the transaction object is in. So we're just going to import it from that memory transaction helper.sol. And in this, there's a function total. And in this, there's this function called total required balance, which basically takes this transaction and figures out how much is required to actually send the transaction. So what we're going to do to check the fee to pay is we're just going to do a uint256 total required balance equals transaction dot total required balance and underscore transaction dot total required balance. And we're going to need to use this library. So using memory transaction helper for transaction like this. So we're going to get this total required balance. And then if this total required balance is greater than address this dot balance, we're going to revert. And of course, we're going to use a custom revert. So error zk minimal count, not enough balance. This, and we'll revert with not enough balance. Great. So that's it. Checking the fee to pay. Does this contract have enough balance? Again, this is where we could add some paymaster stuff. We could say, hey, so-and-so, somebody else has signed up to do the payment, and here's all the logic to do all the payment stuff, but we're not going to be adding any of that customization. We're just going to have the money in the ZK account minimal pay for the transaction. So this is how we're going to check that. And then finally, the important stuff, we're going to check the signature in a very similar way to how we did it with Ethereum. So first, we're going to get a bytes 32. Transaction hash is going to be equal to the underscore transaction dot hash, or excuse me, encode hash. So this memory transaction helper has another function called encode here, where it does some very clever encoding. So one of the most important things is it needs to know what type of transaction is it. Is it a legacy transaction type, which is again type what? Type 0. Is it a EIP 712 transaction type, aka a account abstraction transaction type, aka a type 113? Yes, these are all the same thing. Okay, that needs to be encoded a little bit differently. Is it a 115, aka a type 2 transaction? Is it a 2930, aka a type 1? Yes, there's so many different transaction types. There's also blob transaction, which is a type 3, but it's not supported at zkSync at the moment. Anyways, so each one of these transactions has a different function that actually governs how they are encoded. So this memory transaction helper already helps encode it for us. Boom, we have this encode hash EIP 712 transaction. We already kind of learned about encoding and stuff right now, so we're not going to go deep into it. We're just going to trust that it works. We're going to say transaction hash is transaction.encode hash. This transaction object, exactly like the user operation, has a signature. And this is what we need to validate on it. So we're going to get that signature. We're going to say underscore transaction.signature. And we're going to need to combine this with the TX hash. And we're going to have to figure out how do we actually validate this. Well, exactly the same as with the minimal account. We're going to have to take this transaction hash and convert it to an ETH signed message hash. And what have we been doing? Well, we've been using OpenZeppelin. So we're going to do a little import here. Message hash utils from @OpenZeppelin /contracts/utils/cryptography /message hash utils.sol. Like this. OpenZeppelin, capital H there, so that it actually works. And now that we have this, we can scroll back down and we can do this once again. Message hash utils .to ETH sign, let me zoom in, signed message hash of the TX hash. So we're going to convert this hash to the correct format here. We'll say bytes 32 converted hash equals this. And then we're going to do the classic recover. So we'll say address signer equals ecdsa.recover. And this is where we're going to have to import that as well. Let me scroll back up. Do a little import ecdsa from @OpenZeppelin /contracts utils/cryptography/ecdsa.sol. So we're getting the ecdsa now. We'll call ecdsa.recover, and this will be the converted hash, and the underscore transaction.signature, like this. We'll get the signer. Now that we have the signer, we can check, we can do a little bool is valid signer equals, and all we got to do is check to see signer equals owner, which we actually don't have an owner function yet. We should definitely add this. So let's import ownable as well. Import ownable from @open zeppelin /contracts/access/ownable sol. And we'll make our ZK account minimal is iAccount, and is ownable, which means we need to add a constructor. So we'll add a constructor ownable message.sender. Ta-da. Brilliant. Okay. So it's a valid signer if the signer equals the owner. And if it is a valid signer, then we're going to say this magic. Then we're going to say this magic is the account validation success magic. This is kind of the equivalent of saying true. And we can import this as well. And this from the same place that iAccount is in, account validation success magic. So if it's true, do that. Else, we can just say magic equals bytes 4 of 0. And then finally just return magic. So this is our validate transaction function. Yay. So now, like I said, we are completely ignoring these. So I'm even going to comment them out like this. Since the bootloader is technically going to be the one that calls this, and we'll add some access controls like that in the future, zkSync allows you to do some really crazy customizations with your transaction hashes. So you can have some literally like vanity transaction hashes, which is pretty cool. And you can like save some gas if you have some pre-processing steps with the suggested signed hash, and you can do some other really creative stuff with these two variables. Our code base is going to be super simple, super minimal. So all we care about is the transaction, and we're going to completely ignore these. Make sense? So here's what we do with this validate transaction. First off, we must increase the nonce. Boom! We make a systems contract call to the nonce holder system contract, and we increase the nonce. That's one of the other things that's so cool about zkSync here is we have power over our nonces. We can control our nonces in our smart contracts. Very cool stuff. Then we check if we have enough money in our smart contract to pay. And there is a nice little function that comes with our transactions called total required balance that we can use to make sure we have enough money. And then we do the classic signature checking. First, we encode our transaction struct exactly the same as we did with Ethereum. We use a little helper function called encode hash to actually encode it. Then we convert it to an ETH signed message because we got to have things in the right format. Then we run the ecdsa recover to get who signed this hash. Then we check to make sure the signer is the owner of this contract. And if it is, we say, hooray, we did it. And if not, we return bytes 4 of 0, which is basically the equivalent of saying false. So this is how the zkSync system is going to validate that a transaction sent via account abstraction is valid. Now, the only additional piece we need to add to this is we need to make sure only the bootloader can call this, right? Because we don't want anybody just updating the system contract. We only want the account abstraction system to be able to call this validate transaction and increase the nonce. So we're going to have to create a modifier here, very similar to the only entry point modifier, where we're going to do a little, first off, I want to do a headers modifiers like here. Do a little modifier, zoom in a little bit, modifier, acquire from bootloader. And we're going to say if message.sender does not equal the bootloader formal address. And we're going to import this in a second. Then we're going to revert with zk minimal account __ not from bootloader. Like this, we're going to have another error, zkSync not from bootloader. And then we need to import the bootloader formal address. And guess what? We can get this from the same place as the nonce system holder contract. This is in the constants.sol. If we look for this, boom. Address payable constant, bootloader formal address. So this is where we get the bootloader formal address from. Okay, nice. So we have require from bootloader. Let's make sure we actually add it here. Require from bootloader. Only the bootloader can update our transaction hashes. Only the bootloader can now update our nonces. And we have a way to validate our account abstraction transactions are valid. I always feel like I'm speaking poetry when I say account abstraction transaction. All right, so check. We've done some validation. Cool. After we get all the validation done, the zk-sync node that got the transaction is going to send it from itself to the main node, the main sequencer, and that's going to call execute transaction. So let's now focus on execute transaction and make sure we get this one right. Don't worry, the rest of this will come together and it will make sense. But we're going to call execute transaction because this is where we do the thing. So same thing, we're going to ignore these first two. These are for some cool advanced stuff that we quite frankly don't care about and may never care about, to be honest. So we're just going to comment these out. And we're only going to care about this transaction object. And this is going to be the exact same transaction object that was recently called through the validate transaction function. So execute transaction here. We're going to do something very similar to what we did in the minimal account on Ethereum. So first thing, we're going to take this transaction object and we're going to get the to from it. So address to, and again, we can go into the struct. We can see, okay, what this has, transaction type, from, to, gas, paymaster, nonce, value, reserve, data, signature, blah, 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 all this stuff. We're gonna get the to, we're gonna say to equals address 160 underscore transaction dot to, right? And we have to do this because to is a uint 256. So we need to convert it from a uint 256 to an address. Next, we're going to need to get the value, which if we look in here, value is a uint 256. We're actually going to need to safe cast it to a uint 128. The reason that we have to do that is we might have to use value as a system contracts call, and it takes a uint 128. So uint 128 value equals, and we're going to use some utils here that we haven't imported yet. I don't think we've imported these yet, have we? We haven't imported these yet, but we will. Utils.safe cast to U32, or excuse me, to U128, excuse me. This is transaction.value like this. And we have to import this utils. So the Foundry era codebase has a utils, and let's actually OZ imports, and these will be era imports. Era standing for like zk-sync era imports. So we're going to import this utils library from lib/foundry era contracts /src/system contracts/contracts/libraries/utils.sol like this. And now that we have this utils bin here, we can now call this safecast to uint 128. So we're going to get the value, and then we're just going to get the data. So we're going to say bytes data equals transaction dot data, and we're going to be making bytes memory data, and we're going to be doing something real similar to what we did in our minimal account, right? Remember, in our minimal account, we just did a call. And then if there wasn't a success, we reverted. We are essentially going to do that, but we're going to tweak it a little bit. So for our minimal account, we did it like this. For here, we're actually going to do it a little bit differently. We're going to use assembly. So if we go to the zk-sync docs, call, static call, and delegate call actually work slightly differently. So ideally, we're just going to follow the zk-sync way and do these calls in an assembly block. If you're not too familiar with assembly, I know we haven't really gone over it yet. We have an assembly and formal verification course that you can definitely check out. For now, just kind of blindly follow along with me here. We're gonna have this assembly section. We're going to say success dot or colon equals call. We'll say gas to value, add data OX20, comma mload data, and then 0 and 0. And we'll say, before this, we'll do bool success like this. And this is how we're going to make calls. So this is essentially the same as doing this, just in a little bit lower level language. Don't worry too much about it if it doesn't make sense. And then of course, if this fails, we'll say if not success, then we're going to revert zk minimal account underscore underscore execution failed like that. Go back up to the top, error, execution failed like this. Cool. Now, this is what we would normally do. So this looks pretty good. However, I hate to say this, we do have to tweak this. However, if to was to a systems contract, for example, if execute transaction here was deploying a contract, the to would be to the deployer system contract. And if that's the case, we actually have to call the system contract caller in the same way we did it with the nonce holder up here. So we actually have to tweak this just a bit. So we're going to say if to equals address of the deployer system contract, and we can actually get this from the same place we get the bootloader, from that constants folder. So we'll just import that as well. So if to is going to be that deployer system contract, we want to do something different. So we could do like if to equals any of the system contracts and write some custom code for any of the system contracts, but deploying a contract is a pretty common thing. So we at least want to be able to handle that. If it's to a deployer system contracts, we're going to do uint32 gas equals utils dot safe cast to u32 gas left like this. We're going to do that system contracts caller again dot system call with propagated revert gas to value data. Else, we're going to do kind of this normal call here. So we could put a lot of conditionals for a lot of the different system contracts. For us, we're only caring about deploying. If you want to deploy from this minimal account, this is kind of how you would do it. And since we learned about system contracts a little bit already, you can, if you want to customize this to do even more crazy things with the system contracts, you are more than welcome to do so. But with that being said, we now have the execute transaction function just about done. We do want to add a modifier here because right now anybody can call this. So we're going to scroll up, we're going to add another modifier, and we're going to give this kind of the same powers as our minimal account. We'll say require from bootloader or owner like this. And we'll do if message.sender does not equal bootloader address and message.sender does not equal owner. Then we're going to revert not from bootloader or owner like this. And we'll create a new error right here like so. And then require from bootloader or owner. We'll add this to the actual execute so that only the bootloader or the owner contract can do this. And this is really almost exactly the same as this require from IEntryPoint or owner in our minimal account on Ethereum. Nice. Now with this, we pretty much have our ZK Sync native account abstraction codebase done, which I know is crazy. However, I said nearly because it's not quite done. We still need paying for the transaction in Ethereum happened in this validate user operation. For here, the validate user operation, we just check to see if we can pay. So the actual payment happens down in these transactions here. So let's actually figure out how to do this payment here. So we're not using a paymaster, so we're actually going to make this do nothing. Ta-da, this one's done. Hooray. So prepare for paymaster, we can keep blank. However, we do want to actually pay for transactions here. Otherwise, our transactions will fail. And it's still in that validation phase, actually, before it gets to the execution, that the pay for transaction is called. So this actually happens before that execute that we just wrote happens. So same thing though, we can ignore the transaction hash. We're going to ignore the suggested signed hash. We're just going to focus on the transaction itself. And luckily, once again, in our little memory transaction helper, there's a helper function in here called pay to the bootloader, which will get the bootloader address, figure out how much we need to pay, and then actually pay it. So all we have to do is do underscore transaction dot pay to the bootloader like this. And we'll just say bool success equals pay to the bootloader. If not success, then revert zk minimal account underscore failed to pay. And then we'll add this new error back at the top, error right here. And that's it. So now we can pay for the transaction. We can execute the transaction. We can validate the transaction. We are pretty much done. The only final thing that we want to be able to do is call execute transaction from outside. So right now, if we sign a transaction, we can send it to the zk-sync node as an account abstraction transaction. However, we could also send it as a normal transaction with everything signed and have somebody else just pay the gas fees to send it. And that's what this execute transaction from outside is. No bootloader stuff, no account abstraction stuff. This is like, hey, you can send my transaction and you will pay the gas, right? No account abstraction stuff, just, hey, send this. And we can set this up so that it goes through pretty much the same process as the execute transaction bit here. All we'd have to do is first validate this transaction, kind of the same way we did up here, and then execute the transaction. So what we're going to do is we're going to take all of this here and stick it in its own function. So we're going to do a little return underscore validate transaction underscore transaction. And at the bottom, we're going to create a function underscore validate transaction. It's going to take a transaction memory underscore, actually, I hate the underscore transaction. This will be internal. And I'm going to paste all that code in here. And I guess I'll use the underscore because we're using the underscore in here. And so this is going to do exactly what we did before. Call the nonce contract, check to make sure we have enough balance, get the magic, and then I guess I'll just say return bytes for magic right here. And then boom, we return magic at the bottom. So for validate transaction, in our validate transaction function now, all we're doing is returning this internal function validate transaction. And we can take this same logic, bring it into execute transaction from outside, where we first validate the transaction. And then guess what? Next, we execute the transaction with underscore transaction like this. So let's create another function where we did the exact same thing. Do a little function, execute transaction memory transaction, although I hate that style guide, internal like this. And we're going to take all of this stuff in the execute transaction, copy it, paste it in our function down here. That looks pretty good to me. We're not returning anything. And so now we're going to delete what's inside of execute transaction. Where did that go? Oh, I already did. Okay, nice. And we're just going to call execute transaction underscore transaction like this. And in our execute transaction from outside, we're just going to call execute transaction. So we could 100% say, hey, you're not allowed to do this, but why not? It's going to go through the exact same flow. And if somebody else wants to pay for the gas to send a transaction, great, good for us. We're still checking the signatures work. We're still executing the same way. It's still going to come from our account. If somebody else wants to pay for it, phenomenal. And then the last thing we need to do is, of course, this needs to be able to receive funds. So we'll add a receive function, external payable, so that payable, this can actually receive funds like that. All right, cool. And this, my friends, is our zk-sync minimal account abstraction contract. Let's give this a compile and make sure this works. Forge build --zk sync, and it does. Now, sometimes with Foundry zk sync, I find it has a little bit of a hard time sometimes. So sometimes I will click zk out, and cache, and delete everything in here, and recompile. And this will take a long time to recompile. However, I've still found it can be very helpful just in case you tweak something that was potentially off. And it looks like it has compiled successfully. So I know there's a lot here, and I know we've gone over a lot, and I know we're learning a lot, and I know we're learning at kind of a breathtaking speed here. But this is incredibly powerful work that you're doing. You're enabling yourself to have skills that very few people in the industry have right now, and you should be very proud of yourself. So what we're going to do for the rest of this is we are going to write some tests. Of course, the test setup is actually going to look really similar to what we've already done. There's very little we have to actually learn. We just have to write the tests. However, we're not going to write a script to actually do this like what we did with the send packed user ops. And it's because Foundry scripting doesn't work great on zk sync at the moment. So to actually run this and actually work with this, I actually wrote a lot of JavaScript scripts to actually get this to go, because the JavaScript scripts work very well with zk sync at the moment. So I'm just going to walk you through my scripts once we get to there, and I will actually send a true account abstraction transaction on the zk sync test Sepolia. I highly recommend that you don't do this unless you really, really want to see, because again, you're kind of clogging up the test nets, and you have to get the testnet zk sync Sepolia, which can be really hard to get your hands on. If you want to try this on a local network, I highly recommend you give that a try. And because my scripts here are written in hard hat, I didn't go as hard as I normally do, making the code look very good. Those are our next steps. We're going to write some tests. Then I'm going to show you my hard hat scripts for actually deploying this. Then I'm going to deploy this, and I will show you exactly what this process looks like when you get a successful transaction to run. If you're a little mentally exhausted, now's a great time to take a break. I know I'm throwing a lot at you right now, so it is okay. And maybe if anything in here doesn't make sense to you, it's not clear. It's like, what is he talking about? Paymaster this, system contract that. It's a great time to ask questions. And one of the things I actually really like about the zk sync Discord, if you scroll to the bottom of their docs, they have a little Discord icon. They actually have an AI that has read all of their documentation that does a pretty good job of answering questions related specifically to zk sync docs. It's in their Discord. It's a great tool. Definitely be sure to use that as well. So take that mental break, and I'll see you in a minute. All right, so now that we have our zk minimal account, let's go ahead, new folder, zk sync, create a new file, zk minimal test.t.sol in here, and we will go ahead and start testing this. So you already know the drill. We're going to pop open this pragma. We'll do MIT 0.8.24 contract zk minimal account test is test, like so. We'll import test from forge std/test.sol. We will add a little function set up public in here, and we will get cracking. So if you're following along with the GitHub repo associated with this lesson, in the tests that I wrote, I actually went ahead and I did this kind of setup here where we have, if it's not the zk sync chain, we're going to deploy with the deployer. But if it is the zk sync chain, we're going to go ahead and deploy with new zk minimal account. So we're going to skip this. For those of you watching this in Cypher and Updraft, we showed you this is zk sync chain using the Foundry DevOps tool. For those of you who are watching this on YouTube, you can just kind of ignore this because we're not going to be working with this anyways, at least I don't think. But the reason that we have that is because the zk sync chain, like we've been saying, some of the cheat codes and the scripting don't quite work the same way they do on other EVM chains. So we're going to skip that. The deployment process, if you want to have a productionized deployment process for ZK Sync, you'd have to write some bash scripts, which you can do. You get really creative with your Forge Create. GitHub Copilot and ChatGPT are actually phenomenal at writing bash scripts. They're actually much better at writing bash scripts than they are at Solidity. So you can use that to help you out. So, but in any case, we're going to import that ZK minimal account from src/ZK sync. Did I do a capital S? No, I didn't. I did lowercase. ZK sync, and let's keep that. Let's keep this lowercase down here too, just so that it's all symmetric across the board. ZK sync/ZK minimal account dot sol like this. And then in our setup, we're going to have ZK minimal account. I'm just going to call it minimal account like this. We'll just do minimal account equals new ZK minimal account. Cool. Now we're going to have a whole bunch more setup stuff here, but let's just go ahead and kind of try to mimic what we did with the minimal account tests. Do basically the exact same thing here, right? Because this ZK minimal account is literally the exact same thing as the one on Ethereum, except it has native account abstraction built in. So what was the first test we did for the minimal account? Okay, well, we tested the owner can execute commands, right? And this is where the MetaMask directly calls the wallet and it executes. To do this with our Ethereum account abstraction account, we use the execute command and we sent the destination value and function data. For our ZK Sync minimal account, if we scroll down, what's the function that we have in here? We have execute transaction, which is required from bootloader or owner. And we're going to pass it a transaction object that we're going to go ahead and we're going to build inside of our test here. So let's do a little something similar here. Function test ZK owner can execute commands public like this. Well, we'll do a little arrange act assert because I love to write that. So for arrange, we're actually going to do a very similar setup to what we did with our Ethereum account. So we are still going to need an address destination, and that's going to be some mock ERC20. So let's go ahead and actually import that as well. We can pop back open our minimal account, minimal account test.t.sol. We can grab this mock, copy that line, paste it in here. And I'm just like clicking the line and hitting Command C. I think it's Control C for Linux and Windows. And if you just put your cruiser on the line and hit Command C or copy and then Command V or Control V, that'll copy the whole line and then paste the whole line. So we'll do that down here. We'll actually create a new USDC token. So we'll say USDC equals new ERC20 mock like this. A lot of the setup is actually going to look really familiar to what's in here. So our destination is going to be that address of the USDC. We're going to do a uint256 value equals 0. And we're still going to do a bytes memory function data, exactly the same as what we did in our test over here. Let me scroll back down. Exactly what we did over here. This is going to be abi.encode with selector ERC20 mock.mint.selector. And then what do we do over here? We give it the address minimal account and then some amount. So let me copy this amount line as well. We'll have an amount at the top. And then we'll pass the address of our ZK. And let me do a little toggle word wrap. Minimal account, and then comma amount, like this. Now, what do we do next in our Ethereum account abstraction? Well, all we did was call execute with destination value and function data. However, for the ZK Sync minimal account, we actually have to create this transaction object, which is kind of similar to the user operation. So we created these user operations in the minimal account using some scripting. We don't have a script for this, so we are going to have to create some helper functions in our tests. So I'm going to do little headers, helpers, like this. We are going to have to make a function which creates that unsigned transaction. So I'm going to create a little internal function down here, function underscore create unsigned transaction. And this will take an address from a uint8 transaction type, an address to uint256 value, and then a bytes memory data. This will be internal view, and this is going to return a transaction memory like this. So we don't have this transaction. We're going to have to go ahead and import this transaction struct, import transaction from, and this is from that memory transaction helper thing that we have. So it's going to be lib/foundry era contracts /src/system contracts /library/memory transaction helper.sol. Cool. And if we go back in here, it's this transaction struct, right? So we have to populate this in the same way we had to populate that user packed operation or that user operation, right? So let's go ahead, we'll populate this struct so we can send a transaction to zkSync. Again, this is one of these cool things about zkSync is all transactions are these transaction structs. So let's go ahead and scroll down, create unsigned transaction. Let's go ahead and we'll just do return transaction. And let's open it up and let's just kind of go through this and get it done. Okay, first, transaction type. Transaction type is going to be whatever we pass in for transaction type. Remember, for us, we're going to be doing a type 113, which is aka a 0x71 transaction. But you could 100% have this be, you know, a type 2, a type 0, a type 1, or even a type 3, which is a blob transaction. We have a little video on that as well. But we're going to be doing type 113 for account abstraction transaction. I think I love saying that. What's next? We're going to need a from to gas limit. So we'll say from is going to be whoever we pass in. To is going to be 2. Now about the 2 though, in these transaction type, from and to are actually both uint256s. So we actually have to convert these from addresses to uint256. So to do that, we'll do a uint160 first, and then a uint256. So this is typically how you convert from an address to uint256. You first convert it to a uint160, and then you do it to a uint256. The reason for this is because addresses are actually smaller and they don't really fill up the full 32 bytes, whereas a uint256 fills up the full 32 bytes. That's a much longer that could be a longer conversation. If you're interested, be sure to check out the assembly and formal verification course in Cypher and Updraft. Then we're going to do a little gas limit. We're going to cheat. We're going to copy a little bit of what we did in our send packed user op because we did a lot of this stuff down here. We're just going to use this giant number. Boom. Gas per pub data byte limit. We're going to do the same thing. And this is the maximum amount of gas the user is willing to pay for a byte of pub data. Pub data is published data to the L1. We don't have to worry too much about this one. So we can kind of just pick any value there. We need max fee per gas. We're just going to use this again. We're just basically going to say, yeah, let it all go through. We don't really care. We need max priority fee per gas. We're going to do the same thing. Don't really care. Paymaster, none. We're not using a paymaster. Nunce is going to be the nunce that we get. So we're going to do a little uint256 nunce equals vm.get nunce address minimal account. And this is kind of a cheaty line that doesn't work super well for zkSync because again, zkSync has a nunce holder smart contract that needs to be queried. And this cheat code, I'm not sure at the moment is supported, but hopefully in the future, this automatically gets rerouted to just asking the nunce holder smart contract for the nunce. So for nunce, we're going to say nunce. Value, we're going to say whatever value is passed. Value, which will be 0. Reserved is just going to be this blank array. So this is kind of just reserved for different slots in the future. So for us, we're just going to say uint256 0. We're going to do that 4 times like that. Data is going to be the data that was passed in. Signature, for now, we're just going to leave as blank because this is just getting the unsigned transaction here. And we'll sign this in a little bit. Factory depths. This is something that we're going to learn about in a bit. It is actually pretty important. For now, we're going to leave this as blank. So at the top, we're doing bytes 32, array, memory, factory depths equals new bytes 32, array of size 0. We're going to leave this as blank. It's not important for most of what we're going to be working with. And then paymaster input is going to be blank because we're not using the paymaster. And then finally, reserved dynamic. That's also going to be blank because we're not using the reserved dynamic either. Ta-da. And this is how we're going to get our unsigned transaction here. So we can now take this, go back up here, and we don't need the signature, right? Take this, come back up here, and we can say transaction memory transaction equals create unsigned transaction. From is going to be the minimal account owner. So we're going to say address minimal account dot owner. Oh, actually, we don't even need the address bit. So from is going to be owner. Transaction type is going to be 0x71 or 113. 2 is going to be the destination. Value is going to be value. And then, of course, our function data. So really similar to what we did on Ethereum, except for we're working with this transaction object. Now, since we are calling execute transaction, we actually don't care about the signature because we have this require here, require from bootloader or owner. So as long as it's the owner of this contract, that's the message.sender, this will work fine. So then all we have to do is do vm.prank minimal account .owner, and then minimal account execute transaction. And we're going to have to put some empty bytes 32s in here. I'm actually going to create a static at the top. I'm going to say bytes 32 constant or a constant empty bytes 32 equals bytes 32 of 0. And since we're not using the TX hash or the suggested hash, we're just going to do empty bytes 32, empty bytes 32, then our actual transaction. Boom. And what are we calling here? We're calling mint. So then our final bit here, we can just do assert equal USDC dot balance of address minimal account should now be the amount. All right, let's give this a whirl. So we'll pull up our terminal, forge test --mt, paste that in --zk sync. And we'll have to wait a little bit for this to compile and actually go through. And you will run into this. So as of today, doing a lot of what we're doing, such as kind of making this giant struct down here, working with this transaction memory helper and everything, requires --via IR. So this stands for intermediate representation, and it's a flag you can add to the Solidity compiler to basically have it compile to this middle language called YUL or assembly, and then to the EVM or AirVM. Don't worry too much about that now. Again, we go over this in the assembly and formal verification course. But for now, just in your foundry.toml, just set via IR equals true. And at the moment, this will make your compiles and your tests run a little bit slower. So just keep that in mind, that it will take a little bit longer, but it will allow us to test our code much more effectively here. So we're going to have VIR on true here. It'll take a little bit longer. Don't worry about it. That's normal. But let's go ahead and let's see if our first test works correctly. And after a brief delay, we see our test has passed. Okay, excellent. So our first initial test for our ZK owner commands is successful. Perfect. Let's keep going. So then I would probably test that a non-owner can't execute commands. If you want to go ahead and practice writing that function, you're more than free to do so. But let's actually move on to this more interesting stuff because yeah, it's like, okay, cool. That's not really account abstraction though, Patrick. I would like to see some account abstraction, please. So let's do our validate transaction. So we'll test validate transaction and we'll assert we're getting this magic value, right? So we have this validate transaction here, and this magic should return this account validation success magic. We should make sure that we are getting this as a valid signer, right? So if the signer is the owner, we're going to say it's a valid signer. Otherwise, we're going to get this empty bytes for. So let's do a new function, test zk validate transaction. Make this public, scroll down a little bit. Might get a Copilot is already trying to figure it out for me. Arrange, act, assert, like this. So we're going to copy a lot of what we've already did. Same is kind of what we were doing before. We're going to get the destination, the value, the function data. We're going to be calling mint to the minimal account with this amount. We're going to be doing the same thing. We're going to generate the unsigned transaction here. And now we actually need to sign this transaction, right? We didn't need to sign it up here because our validation for execute transaction was just, hey, is it the owner or is it the bootloader? In either case, go for it. But now we need to call validate transaction, right? Because now we're going to be simulating a true account abstraction transaction. Scroll back up. What's the process look like? Well, the first thing it does is it checks the nonce holder. Then it will call validate transaction. So anytime on ZK Sync, you send an account abstraction transaction. I don't know if I love it or I hate saying it. It's going to call validate transaction first. So we need to sign this transaction. So we're going to have to create a new helper function called sign transaction. So let's do that. Function underscore sign transaction. And this is going to take a transaction memory transaction. And then also, so this is going to be the unlocked account doing the transaction. Now with doing this, we're going to actually run into the same issue that we had with send packed user op, right? So when we signed the transaction with send packed user op, if we had an unlocked account, we could use config.account, no problem. But when running locally, we had to use a default Anvil key because why? Well, when you run your tests, Foundry doesn't assume that you have anything. So we're going to have to do a similar setup here. And since we are also just using tests here, what we can do additionally is kind of cheat a little bit more. So I'm going to leave this as a count. However, we're going to kind of super cheat here, and you'll see what I mean in a minute. So what we want to do in here is first, we're going to want to encode this transaction. And to do that, remember we have that memory transaction helper dot encode hash transaction, code hash transaction. And we should import this if we haven't already. Boom. And it's this function again that helps actually encode these, right? We can go back to this. We can see that depending on the different transaction types, it encodes them all like a little bit differently. So we want to encode it correctly. So this will give us the bytes 32 unsigned transaction, unsigned transaction hash. Like this. Then we can get the bytes 32 digest. We now have to convert this into an ETH signed message. So we will say unsigned transaction hash dot to ETH signed message hash like this. And since we're doing to ETH signed message hash, we're going to have to scroll up to the top here, and we're going to have to do a little using message hash utils for bytes 32. And we're going to have to import that. Import message hash utils from at open zeppelin /contracts /utils /cryptography /message hash utils.s.sol, and using message hash with a capital H here. Cool. Looks good. Then we can scroll back down. Cool. Then we get the digest at the bottom here. Now we can do that actual signing, kind of the same thing that we did in the send packed user ops. And I'm actually going to even copy this a little bit. I'm going to copy the vm.sign Anvil key digest. I'm also going to copy the Anvil key and the VR and S. Anvil key and the VR and S here. So we could 100% again do like if, block.chain ID equals 31337 or equals 31337, and then use config.account, yada, yada, all that stuff. But since we're never actually going to run this test on an actual network, because again, scripting doesn't work with ZK Sync, we can kind of safely assume that this is always going to be just running locally. So we can actually even just dump this account here. And we will say for this code base, we should have our minimal account owned by the Anvil default key, the Anvil default user. So in send-packed user opt, we call with the Anvil default key, and back in our minimal account test, if we scroll up to the top, or excuse me, if we go to our helper config, we're going to use this Anvil default account. We could import it from our helper config, but again, this is our test. We know it's going to be a little bit different. So I'm just going to kind of copy paste it here. And what we're going to do, oops, sorry, this is the wrong, make sure you're on the right test. So I'm just going to kind of cheat, paste this at the top. And what we're going to do is when we deploy our minimal account here, we're going to do minimal account dot transfer ownership to the Anvil default account. That way, since the minimal account is owned by the Anvil default account, we can actually sign the transaction with the Anvil default key. So a little bit of a workaround here. Like I said, I have an issue in Foundry. Hopefully somebody takes it on and actually makes this improvement here. If you're watching, like I said, this is a great opportunity for you to contribute to Foundry. But okay, so we're getting our V, R, and S here. That's looking very good. Then we can do transaction memory signed transaction equals. So we're just going to set up signed transaction to kind of make it look different. And we're going to say signed transaction dot signature equals ABI dot encode packed. Remember, this is RSV. Remember, we get VRS, but then we have to go RSV to actually do the signature here. Remember, the order is important. And then return signed transaction like this. So this needs to returns transaction memory like this. Cool. Signed transaction like so. What's it matter about? It can be restricted to view. Yeah. Okay. We'll make this view. And now that we have this signed transaction, we can scroll back up. We can do transaction equals underscore sign transaction like this. And so now, just with that, we have a signed transaction struct. And if you want, you can even do like a little like console2.log of the transaction.signature.data, transaction type, whatever you want. So you can see kind of this transaction struct populated. But now finally, we can do the act. So we have this signed transaction. And remember, the process for doing account abstraction on ZK Sync is first the bootloader or the ZK Sync Lite client or the ZK Sync API client is going to call this validate transaction function. So we need to simulate being that ZK Sync node. And the way we do that is we prank the bootloader formal address. Remember, that is another system contract. Anytime you have a ZK Sync node interacting with system contracts, the caller is going to be, the message.sender is going to be this bootloader system contract, right? Because it's this super special admin smart contract. So we're going to do vm.prank bootloader formal address like this. And so we need to get the bootloader formal address. So we're going to import that from that constants area. So I'm going to import bootloader formal address from lib/foundry era contracts/src/system contracts/constants.sol like this. And so now that we have the bootloader formal address here, we can finally say, okay, bytes for magic equals minimal account dot validate transaction empty bytes 32 empty bytes 32 and transaction. Because again, for our validate transaction, we're ignoring the TX hash, we're ignoring the suggested signed hash. Again, uses some fancy smancy things that we do not care about. We're just focused on the transaction itself. And then we can finally do assert equal magic should equal this. Where is it? It should be this account validation success magic. And so we can actually grab this from our IAccount.sol. So we're going to go ahead and we're going to import that in our test back at the top. We'll do a little, actually, OZ imports. Here's your 20 mock era imports like this. We'll import account validation success magic from lib/foundry era contracts /src /system contracts /interfaces /iaccount.sol. Ta-da. Now, if we scroll down, we can do assert equals magic account validation success magic. Mwah. Beautiful. If this test passes, it means we are doing something very cool. It means we are creating an account abstraction transaction, and we are able to sign it correctly and allow the zk-sync nodes to say, yes, this is a valid account abstraction transaction, and you can go ahead and push it through. So let's run this test. We do forge test --mt, paste this in, --zk-sync. Remember, running this with our foundry.toml, having the via IR is true. If you do not have that in the foundry.toml, you can also do --via IR like this, but we have it in the foundry.toml. Now, as of recording, originally we could just do is system equals true in the foundry.toml. As of recording, the latest update of Foundry zk-sync, this is no longer the case. We now have to pass it directly into the command line. I'm sure that at some point this will change and we can add this back into the foundry.toml. But for now, we actually have to do forge test --mt, paste the name of the test --zk-sync, and then we also have to do --system mode equals true like this. So this --system mode is the thing that's going to allow us to call a system contract. And if we don't pass the system mode, if our system mode contracts aren't working, then we're going to get some weird EVM revert errors. So if you run into weird EVM revert errors, definitely be sure to make issues on that Foundry zk-sync project, because it's an alpha and the feedback will be very helpful, and it will enable you to deploy zk-sync smart contracts even easier in the future. Or you can go ahead and try to contribute to Foundry zk-sync. That is a great place to start your Rust development career. And again, this will take a little bit of time. Oh, and then actually this makes a lot of sense. We're getting the not enough balance error here. This is an error that we can definitely understand. We have to do a vm.deal, that minimal account, some amount. We'll do uint256, constant amount equals 1 E18. That should be more than plenty. Address, minimal account, clear, and rerun. And it has passed here. Okay. Incredibly exciting. So we've tested our validate transaction actually works, and we've tested our execute command also works, which means if we go back to the ZK minimal account, if we scroll back up to the top here, it looks like we've actually gone through our whole process. ZK API calls validate client, which must update the nonce, checks the nonce has been updated. They call pay for transaction, which I guess technically we actually did not test this. However, for this demo, I'm going to say we can go ahead and skip that. Obviously, if this was a real code base you were working on, you would 100% want to test that. Then API client verifies bootloader gets paid. The API client passes the validated transaction to the main node, and the main node calls execute transaction, which we've already tested works correctly. Now, we could then go ahead and test execute transaction from a side, but I'm going to go ahead and skip this for now and just say, guess what? Huge congratulations. You've just written the tests and built a zk-sync minimal account abstraction account. This is incredibly exciting. Now, a couple of points on running the whole test suite here. If I just run forge test at the moment, what do you think is going to happen? Without the --zk-sync, without the --system mode equals true. Of course, we get some reverts, right? Test zk validate transaction, of course, fails because we didn't run with the --zk-sync flag. We didn't run with the system mode turned on. So it of course fails. I have gone ahead and in the actual GitHub repo associated with this course, I've added some of these checks in here, like if not ZK Sync Chain, if it's not ZK Sync Foundry, to make it a little bit easier. But I don't think it's super important for your learning experience to go through adding all these conditionals in here. So if you want to update your code base to reflect what I have, feel free to just come into the minimal account abstraction code base and copy paste the changes directly from the script. So, and when you're using this repo as well, just also be sure to, whenever you run commands, be sure to use the commands that I've added in the make files. I've set it up so that a lot of the scripts that you're going to need to do are already in here, and you can just run like make deploy or make ZK build or whatever that needs to be done here. So cool. Now the final piece that I want to show you all is actually deploying and sending an account abstraction transaction. Now, like I said, as of today, Foundry scripting on ZK Sync leaves something to be desired. So the best way to really do deployments is using hard hat. So we don't cover hard hat in Cypher and Updraft, so I'm not going to walk you through actually deploying to ZK Sync with hard hat. I'm not going to walk you through actually setting this up and deploying this and running with this, but I am going to show deploying the account abstraction contract to ZK Sync and then sending an account abstraction transaction to ZK Sync as well, which is really cool. And if you are familiar with JavaScript and hard hat and Node.js and TypeScript and stuff, and you want to run these as well, feel free to do so. But I'm actually going to jump cut over to me copy pasting all these scripts into my local file here so that we can actually deploy this. All right, and actually before we actually send this out, I do need to make two little tweaks that make the JavaScript a little bit easier. We were erroneously doing this message hash utils.toEth signed message because I didn't realize that in this encode hash function that we're doing here, down here, it's already putting it into the correct format, like so. We actually don't need to do this bit right here where we do message hash utils.eth signed message. So my mistake. In our test as well, message hash utils, we don't have to do this step. This is already a digest right here. I didn't realize that this encode hash actually already returned that. So sorry about that. You can comment or delete those lines. And one more tweak as well. When we call validate transaction in execute transaction from outside, we definitely should check the magic that is returned here. Right now, we're just kind of saying, hey, looks good to me. This is actually a pretty common security issue for signature stuff. So we would do like bytes for magic equals this. And then we would say if the magic does not equal that account validation success magic, then we would go ahead and revert with pretty much whatever we want here, like error zk minimal count invalid signature, like this. Revert invalid signature. Boom. Because we want to make sure that magic value that is returned is actually correct. Okay, now that we've done the final tweaks here, let's go ahead, let's deploy this, and let's do this. So first we're going to run this yarn deploy command to actually deploy that ZK minimal smart contract. And we've done it like so. So we're going to grab this. We'll go over to the ZK6 Sepolia. We'll paste this in and we'll see, we do indeed see a contract here. And this is our ZK minimal account. Now we can't actually verify this contract as of recording because as of recording, any smart contract that interacts with system contracts can't be verified. So this is just, it is what it is. But then what we're going to do, we're actually going to send this some funds. So I'm going to paste this in here. I'm going to send it 0.001. That should be more than plenty. We'll confirm. I wish I had this much money in my wallet. That would be great. This is one of my burner accounts. ZK Sync was kind enough to send me a bunch of testnet ZK Sync so I could make this videos for you all. Great. So now that we have this, we're going to take this ZK minimal address and we're going to open up the send AATX right here. And we're going to paste this right at the top, this ZK minimal address. And if this goes through successfully, we will see a transaction on here that is from this wallet address, believe it or not, even though this is a smart contract wallet, which is crazy cool. So let's go ahead and do a little yarn send TX, and hopefully this goes through successfully, and we will have done it. And it's looking pretty good. Transaction sent from minimal account with hash. This hash right here. Let's go ahead. We do a little refresh on our smart contract now. We now see we have indeed a transaction right here. It's probably going to be the same one that we just created. Yep, it is. And it sure is. We can see the from is this wallet here. And this is the smart contract wallet that we just deployed. That's crazy. So on ZK Sync, you can literally have the smart contract wallet be the from, which is not possible on a lot of these other chains. Really, really cool. And we've done a very simple approval on the fake mock USDC contract that we actually deployed. Wow, this was a lot, but hopefully you can see how powerful this is. On ZK Sync, you can have a smart contract wallet that also acts like an externally owned account with account abstraction built in. So we have learned a ton, because not only do we learn how to do this on ZK Sync, we also learned how to do this on Ethereum. So we learned how to do account abstraction on a chain that doesn't have native account abstraction, but has account abstraction via an IEntryPoint smart contract and an alt mempool. And then we also learned how to do account abstraction on a chain that has account abstraction built in. This is wild, and this is incredibly powerful. So before you jump off, let's do a quick rundown of all the crazy things that we just learned, because we've just learned some really, really powerful stuff. So first off, we learned what account abstraction even was. We learned that essentially account abstraction is saying, okay, instead of a private key signing everything, you can have whatever you want sign anything. It could be a Google session key. It could be a group of friends. It could be the weather. Account abstraction is the concept of anything being able to validate your transactions, as long as you code that anything into a smart contract. Traditionally, only private keys can sign transactions, but with the power of code, we can have anything sign a transaction. On Ethereum, the way that you have to do this is you first have to deploy a smart contract with that anything codified somehow. Once you deploy that smart contract, you can send an account abstraction transaction by signing the data off-chain, sending it to an alt mempool of nodes, who they will then submit it to the blockchain to an IEntryPoint.sol via a function called handleOps. The IEntryPoint will work with some extensions like a paymaster, a signature aggregator, and then it'll send the transaction through your account where you will interact with a blockchain, etc. We built a very minimalist version of this in our minimalaccount.sol. The only function that these smart contracts must have is validate user operation, where they take a packed user operation struct, which has all the stuff that's needed for a transaction to happen. We added a couple of really important pieces. We added a function to execute, so our smart contract could actually do stuff. We, of course, have validate user op, where we used validate signature down here, where it was very ECDSA recover, just to check if the person who signed the packed user operations is the owner of this contract. We, of course, added a function to pay the bootloader to pay that IEntryPoint contract, because you need to pay somebody, because you need to repay those alt mempool nodes who sent the transaction. And that was it. And we built some really robust tests for this on Ethereum. And then we also built some really cool and robust scripting for this. That was how it worked for Ethereum. For ZK Sync, it works a little bit differently, because ZK Sync has account abstraction natively built in. For ZK Sync, you don't have to send to an alt mempool. All you have to do is codify your rules, your signing rules, and then send your transactions as a type 113, and ZK Sync will handle everything auto-magically behind the scenes. So in order for us to make a ZK Sync minimalist smart contract, there are a few other pieces we needed to add. So we need, instead of validate user ops, we have validate transaction, because on ZK Sync, all transactions are of this struct transaction type. So ZK Sync will always pass your transaction to this validate transaction function. We also added an execute transaction from outside. These are the functions that will enable our smart contract to actually do stuff. We added a pay for transaction and prepare for paymaster as well to interact and deal with the paymaster. In our ZK minimal account, we had our validate transaction, which was a really basic function down here. We increased the nonce by interacting with a system contract, which was something that we hadn't learned about before. On ZK Sync, there are a lot of admin smart contracts called system smart contracts where they have admin level power. They have power over the global state of the chain and can do really cool stuff. We made sure we had enough money. And then we also did a very basic ECDSA recover on the signature and returned the magic as such. We then had a very basic execute transaction function, which just had a little bit of a conditional for if you wanted to interact with a deployer system contract. For this, we also wrote some really cool tests, and we had to make sure that we used forge build -zk sync -system mode equals true. And depending on when you watch this, this key might be a little bit different. We might actually be able to have this in the foundry.toml, but as of today, that's how we had to do it. We wrote some very basic tests for this as well, and we didn't write any Solidity scripts because Solidity scripts don't work great with ZK Sync at the moment. So what we instead did, we kind of cheated a little bit. We watched me actually deploy this contract with some JavaScript stuff that I wrote previously, and then also send the account abstraction transaction myself. If you're following along with the GitHub repo associated with this course, if you scroll down into here, you can actually go and see the examples. Where are they? Examples. You can see the example deployments and the example transactions that we ran if you want to take a look at some of the coolness. Some of the big differences between having native account abstraction and normal and entry point based account abstraction is that entry point based account abstraction, the from is going to be whatever node or user actually created the transaction. Whereas on ZK Sync with native account abstraction, the from is actually going to be the smart contract wallet itself, which is really cool. So I know there was a ton of code, but you learned an absolute ton. And a lot of people do not have this power unlock for their smart contract development journey. I highly recommend you take a minute, or several minutes actually, you take a break, you go get a coffee, you go to the gym, and maybe you try to build an even cooler account abstraction code base. Account abstraction is a great way for Web3 to scale adoption because we can actually code smart contracts that are more user-friendly, have easier login, have easier validation, and just have a lot more flexibility and granularity with how transactions are signed and interacted with. To me, there is a $10 billion company in this account abstraction idea somewhere, and it's up to you to go out and figure out how to build it and figure out how to scale it. So with that being said, take a break, go to the gym, go get some coffee, go get some ice cream. You have done phenomenal getting this far.